Check 1, 2, 1, 2. Here we go. Dat willen wij even gehoord hebben.
All right. Good morning, everyone. Yeah, thanks for joining this session. We have our first presenter for today. We'll be having actually 6 speakers today. Tilman is the first one, coming from TU Delft, and he'll be talking about how to advance, basically advancing the program synthesis within Julia, and about the package on the herb.gl. So let's give it up for Tilman. Yep.
Does this work? Yeah, okay. Hi, I'm Tilman. I'm, as said, from TU Delft. I'm a PhD student there. And today I'm going to talk about a library that we developed, which is called herb.gl, named after Herb Simon, the founding father of program synthesis. And I'm going to talk about how to teach programs, how to program, actually, with program synthesis. So why should you listen to me? So first off, wouldn't it be great, like all of us love to program in Julia or in Python respectively, wouldn't it be great if Julia just does it for itself? Like this process can become tedious at times, so you just give it a description of what you basically want. Julia magic happens, and suddenly your satisfying program is spat out. Well, this is still a far-fetched dream. This is the task of program synthesis. So what do we do in program synthesis? First off, we need 2 ingredients. First off, we need a description of what we want, which we call a specification. This can be all sorts of things, from examples, like this is the very common example from Excel that you might know. So this funny little dot at the bottom part that you can then drag down and then auto-completes everything. This is like an application from 20 years ago of program synthesis. And the second ingredient that you need is a grammar, which basically describes your language that you can use. If you're not a computer scientist, so you have symbols on the left-hand side, and then you can iteratively and recursively substitute these things, and hence generate more and more programs. S is an abbreviation for string in that case. But this grammar can be anything. This can be Python, this can be Julia, but this can be also something highly specialized like this, or it can be something totally different, which is not a program at all, like differential equations or whatnot. And then we are able to generate programs like this. So this is then a program that we can then introduce, apply to our inputs, check whether it matches our outputs, and so on. So why herb? The field of program synthesis is an absolute mess, in to put it euphemistic. So program synthesis has been around since the early 60s, is one of the older topics in classical AI, so to say. And every single research group is basically cooking their own soup. There are so many methods out there which are just straight up not usable by anybody else. They're in absolutely obscure programming languages, like Java, for example, and they're very hard to run on anything, or are even proprietary, for example, from Microsoft or whatever. And the second issue is that benchmarks that you want, when you want to actually do something with them, they're in even worse programming languages like Stack and whatnot, languages that you never heard about. So we made an effort to come up with a framework where you can actually use existing synthesizers, run them in your benchmark or your problem in a, well, human-readable form, which you will see in just a second. So herb.gl is a Julia framework that provides a unified and universal approach for program synthesis, which lets you define what a program is, what the problem is, and so on. We implement, or we give a few building blocks, which then help you to implement your own synthesizer or re-implement existing ones. And third off, we provide a bunch of state-of-the-art benchmarks and synthesizers for your kinds of problems. So, how does this look like? How do we do this? So this is a way of defining your problem. The sheer fact that we are able to put this on a single slide, which you're basically not able to do with any other program synthesizer, and it's actually readable. You can actually understand what you're doing. So I basically just translated the example that we've seen earlier on into a little bit of code. So it's basically the exact same grammar. We define our problem, then we add a constraint, which I will explain in just a second. Then we introduce our iterator, and then we just call synth, and we have our program. That's how simple it is. Okay, but how? So basically what we do is we describe a bunch of utilities. So basically, what is a grammar? What is a specification? How can this look like? What different forms can this take? And how to run different your generated programs. So how to interpret Julia, how to interpret Python or whatnot. And we also provide a bunch of benchmarks. And then we also provide an efficient search method for this, so how to efficiently enumerate this, and Julia helps quite a bit with this. There's two ways to go about this. So there's this program space opened up by the grammar, and there's two ways to go about this. So there's constraints which you can introduce, which basically narrow down your search space. So for example, if you have an addition, there's symmetry breaking, which basically, because addition is commutative, you don't have to explore the same program twice. And there are like different search methods which can facilitate this or accelerate this. For example, heuristics, this can be an LLM of your choice. I'm a little bit opposed to LLMs, but this can be any naive heuristic that you can actually, that you want to use. And then you can synthesize your program. So what do we have right now? We have an efficient representation and efficient enumeration of programs already existing. We have a working constraint system. If you're coming from constraint programming, this is actually a very cool novel system which we're going to publish in a couple of months. And then we have a cool set of building blocks to implement your own synthesizers in a few lines of code. What's next? We have to re-implement a lot more synthesizers actually. That are already existing and known to be well working. We need more applications and benchmarks, which I will get to in just a second. And then we are also currently working on a smarter integration with LLMs, which is not just calling ChatGPT to try to solve your problem. If you want to grow herbs yourself, we have a marvelous garden. Obviously, it's a garden where you can grow herbs. It's funny. If that sounds interesting and you're tired of writing code yourself, or writing differential equations yourself, or basically anything like modeling yourself, we can try to do this for you if you have a specification of doing this. So if this sounds interesting, or you want to contribute, or you have cool applications that you would like to see in action with this, or you're just generally curious about herbs in general, but also specifically HerbJL, then please come and join. This is us. I'm one of the developers, and there's like 40 more developers, or has been more than 40 more developers over the last 1.5 years, which we're developing this. There's also Sebastian in the crowd here, and so on, if you have any more questions. Also, we have a big QR code if you want to check out our website. We've been trying to make this as presentable as possible, but if you have any more questions, you find contact details over there, and so on. And if you have any questions, I'm open for that as well. Thank you very much.
All right, any questions? Awesome.
Thank you for the presentation. It was very cool. So your work seems kind of more fundamental at the moment. You mentioned the applications. So what you're doing right now with the Excel thing is like, you know, splitting a string on a dot and getting two elements. It's nice that it works, but do you have any cooler applications in mind that you're working towards? Or are you just more interested in the fundamentals?
So where this actually shines is, like, this is not going to develop your entire code base. This is not going to work. I mean, maybe it will. But where this actually shines is if you have, I don't know, what you may know as test-driven development. Like if you have an actually good description of what you want, this will be able to generate it for smaller-ish functions. So we recently talked, for example, to a bunch of people at CERN who have real struggle finding developers, for example, for their obscure programming language, because like you need people who know physics and know programming, for example. And the crux about this is that you do not care about the programming language actually. Like it doesn't matter. You just search for it, and if you're able to, then you're able to. Yeah, and this works-ish. I don't know. For smaller programs, yes, but for anything basically, if that's cool enough.
Thank you.
All right, we have one more question, and then we'll switch to the next speaker.
Sure.
Just a quick question. Why do you split up your herb into so many sub-libraries, like herb search and so on?
Yeah, we had numerous discussion whether to put this as a big monorepo or not. I think the reason for now is to have this in a modular way is just the development stuff. So we have a lot of different projects and a lot of students working on different subparts of it, and it's just a lot easier when you have like, so in the last 3 months we had like 20 people working at the same time on this. If you want to manage much better if you have this in a modular way, so you can actually try to merge just the subcomponents and not everything all the time. Sure.
Okay, yeah, let's give the final round of applause for Ilman. Thanks, that was a great presentation. Yeah. Okay. Okay, our next speaker is Lucas. He will be talking about FMI compliant for that integrates with differential equations.gl. So yeah, I'm looking forward for this talk. Okay, fmiexchange.gl. Okay, Lucas, let's give it up for Lucas, and yeah. Go.
So, hi everyone. So my name is Cas, and I'll be talking about the package that I've developed called fmiexchange.gl. And this is really a package, if you've ever used functional mockup units, you know it's not fun. I try to make this a bit more usable and user-friendly. So let's talk about it. So if you're anything like me, you are working together with somebody, some department, somewhere in your company or even in another company that is used to having a lot of models in Modelica, and they love it, and they built their whole tool chain around it, and you've never heard of this language, and suddenly you need to work together with these people. And they tell you, oh, that's not a problem, because we can export our models into this binary format, which is, by using the FMI standard, you can make a bunch of binaries that runs your model. And it's called a functional mockup unit or an FMU. So you think, okay, great, I can work with binaries, no problem. But before you know it, you're reading a 100-page standard about how this binary is supposed to be called, in which circumstances, and it's really just not very usable, just coming out of the box. And yeah, luckily, I'm going to talk to you today about how you can avoid this, and we'll be doing that through a demo where we'll be simulating the thermal dynamics of a residential building, and we will be trying to make an observer to estimate some hidden states in this building as well, which opens, of course, the avenue for advanced control methods. We will be using the fmi.gl package, which I didn't write myself, which was written by somebody in the back there, to handle the FMUs. But we'll be using fmiexchange.gl to avoid handling any FMUs, which is far superior, in my opinion. So, if you don't know what is a functional mockup unit, it's basically a differential algebraic equation packaged in a binary. You have some inputs, pi, you have some outputs, po, and you have some states, u, which are basically all the variables which are differentiable. And you also can have some events, of course. Now, you can solve this using a solver which is packaged with a functional mockup unit, which is called co-simulation, or you can use an external solver like differential equations. And that is what we'll be doing today. It's called model exchange. So you got your functional mockup unit from your colleague somewhere in civil engineering or mechanical engineering, whatever. The first thing you need to do is find out, okay, what is actually in here. And for that, we can just use the existing fmi.gl package and call the fmi info function. It will give us a whole bunch of data here. What's most important here is you have inputs, outputs, and states. Every input has a certain address inside the functional mockup unit and some names associated with it. So you can see there's multiple names for each address, which can make it nice and confusing. In our case, we have 3 inputs, which is just some time series data in the end. And here are control set point for the heat pump inside this building. Our output is then the indoor temperature of the building, and we have some states which we don't really care about, but we need to integrate them to make the model work. So if you want to just simulate this using fmi.gl, it's kind of a nice experience. You can provide this 3-line input function, which is just taking the time and a vector as argument, and then you just mutate the input vector with the numbers that you want. And internally, this is then all packaged into an ODE problem and sent to differential equations. So you can see it's kind of easy to do this because you have only like a very simple function that you need to write. But when you want to do some more advanced stuff, like applying a controller, say I want a digital controller which is triggered every hour to reset the heat pump, well, it becomes kind of more complex. We now have 3 arguments in our input function, And the C component here, this is really the functional mockup unit itself, which is passed. And this can sometimes be nothing, so you need to handle this edge case, which is happening at the start of a simulation. When you do your control, you want to check whether actually this function is called at the right time. So you don't want to do it every time that your integrator steps, you want to do it every hour. And then when you want to get like a temperature measurement, you need to do this FMI get real function, so you really need to interact with this functional mockup unit object. And this is of course a very easy example still, but you can see if you want to do more advanced things, you kind of need to read up on the standards, it's not so nice. So at FMI Exchange.gel, I took a fully different philosophy. Simulate models, not functional mockup units. What is a model? It has inputs, outputs, and states, just like a functional mockup unit. It can provide you with a derivative function, an output function, maybe some callbacks, just like a functional mockup unit. But it's not limited to functional mockup units. And the whole simulation philosophy is that all your inputs and outputs, they are stored in the P vector that you would use in the differential equation simulation. And of course your states, they are stored in the U vector and the DU vector for the derivatives. And if we then want to write the same program that we just did in FMI.gel, you can see we follow a quite standard workflow. So first we load the functional mockup unit and wrap it in a model. And then we can just start making callbacks. For example, applying our time series, we can do this after every integrator step with a function calling callback. We can apply our controller fully separately with a periodic callback, so you don't have this annoying if statements in your input function. And then you can just create a callback set, make some initial conditions, and call the solve. Now, two additions to the callback set here is that you need to apply the output callback, which is just keeping the output of the functional mockup unit updated during the simulation. And then the get callbacks is just any events within the functional mockup unit itself. So let's say that we now have our basic controller. We want to create an observer to estimate the hidden state in our functional mockup units. We can use fmi.gel to get the Jacobian, and then linearize around this with controlsystems.gel to create an observer and create our own differential equations compatible observer function, like we usually would. And really the strength of the approach here of simulating models is that now we can simply change our ODE function to include both the functional mockup unit and the observer. And you can see that we can now simulate both at the same time. So we have these temperatures here, but also you have here the hidden state, which in the observer is converging towards the real hidden state. So this is already much more than what we could do with fmi.gel. You can now simulate multiple models together, multiple functional mockup units, multiple Julia models. You don't really care what's in the model, like how it's built, you just care about the content of the model. And this was not previously possible with fmi.gel, where you could just package this input function and not really a different differential equation. Now, one problem here is still we have like a lot of indices that you need to specify manually. So in FMI Exchange, we have some rudimentary address mapping functionality, which just makes some dictionaries with symbols. And you can rewrite this using these dictionaries. It's a bit more readable. It's not quite the functionality of Modeling Toolkit, but then I am also not quite Chris Rokakis. So just to summarize, fmi.gel is amazing for working with functional mockup units, and it's great if you have simple simulations with a single functional mockup unit inside. And if you know how to work with the FMI standard, this is really what you want to use. If you don't want to have anything to do with the FMI standard, you can use FMI Exchange.gel because you can use the differential equations interface, and you're working more on a model-based approach than not a functional mockup unit-based approach. And you can really say like, okay, I'm composing multiple functional mockup units, multiple Julia models together. And that's really the core. So check out the package, which is this QR code. And I have a bit more extensive demo in this QR code if you want to. So thank you for your attention. I'll be taking any questions.
Right, thanks a lot. We have time for one question. Actually, so anyone? Well, Yeah, that was actually quite interesting to see how you. I have one question about the scaling with the number of models you can integrate simultaneously. Like how does it scale? Like the
I didn't really test it for very many functional mockup units, but it should scale quite well. The way that works is that has some caching going on because it's in the end calling C functions, and they are only operate on vectors of floats, so not subvectors and stuff.
Okay.
So you have there a bit of a memory bottleneck that you need caches for every functional mockup unit. But for the rest, I think, I mean, it should be the same. In the end, it's just a bunch of structs which wrap the interface. So it depends on how good are your functional mockup units. If they all have memory leaks, then yes.
Okay. Okay. Yeah. Thanks a lot. Let's give the round of applause for Lucas. Yeah. Thank you very much. Okay. Our next speaker is Francesco from the University of Leipzig. He'll be talking about spectral indices.gl. Yeah, let's give a warm welcome for Francesco. And yeah, good luck.
Yeah. Test. Okay. So in this talk, I will present spectral indices.gl, part of a work of a collaborative effort going on at Leipzig University. Before that, though, I want to quickly talk about what spectral indices actually are. So they can be broadly be defined as mathematical combinations of reflectance values from different wavelengths or bands, and we'll be using wavelets and bands kind of interchangeably in this talk, of satellite or aerial imagery. And these spectral indices are used to enhance or mask different surface properties. So you have the satellites looking down on Earth and getting some values back, and from these values you actually want to investigate certain properties of the Earth system. But to have like a clearer idea and actually a picture of what's going on, here we can see the reflectance values of different materials that you can find on the land surface and the wavelengths or again bands associated with them. And you can see there is the visible spectrum of colors on the left side, but also satellites and other drones can go further than that and see a near infrared and also a shortwave infrared, number one, number two, different values, so different wavelengths to which correspond different values. And what do we mean by mathematical combinations? Well, that's actually pretty straightforward. Here we have an example for the near-infrared bands and red bands recombined to what is called the NDVI, or Normalized Different Vegetation Index. It's kind of a well-known index used for investigating vegetation properties. And as you can see, it's a simple, clear mathematical expression. And so it doesn't seem to be so harmful. What is the problem? That spectral indices lately have been increasing in number. I don't know if you saw the date on the citation of the NDVI, but is 74. And since then, there's been an increasing number of vegetation indices, spectral indices, for multiple reasons. Some of them are that there are new missions with different bands. So novel satellites are going up and observing different bands, and these bands are used to they are recombined into different mathematical expressions to investigate different properties. And novel indices and or modification of different or existing indices are also pretty common. So for example, again, going back to the NDVI, because I work with vegetation, so that's what I know best. There's been a modification quite recently in the literature, 2020, 2021, of kernel NDVI. Again, these are small modifications, but they are increasing in number. So if you want to actually stay up with the literature, I feel like that the situation at the moment is really confusing, and you have to be careful about looking at a lot of different papers and a lot of different implementations of different indices. To go and actually try and solve this problem, there have been multiple collection of indices. Here we have the index database, some examples, in indices gallery from Esri, and the alphabetical list of spectral indices. And all these lists try to do the same thing, but they all have different problems. So for what we wanted to have from a list of indices, so for example, if I remember correctly, the alphabetical list of spectral indices doesn't have the citation from the paper to which they take a spectral indices. The index database is not open source. You cannot modify or suggest new indices. So in order to provide something that was open source and more complete, so under different aspects, we proposed, we created a collection that's called awesome spectral indices. And in this collection, you have a list of machine-readable spectral indices with different properties. And connected to that, yeah, okay, sorry. And here you can see the one entry again for the NDVI, because that's the one I know best. That's one entry, and it's clearly machine readable. It's a JSON file in which you have all different properties of the spectral index. For example, like the application domain, which bands you're going to use for this index, and also the bands are going to follow are following a standard that's already well defined in the literature. And you also have, more importantly, the formula expressed as a string. And there is a larger and broader ecosystem in the awesome spectral indices suite, and there is a Python package to access and compute these indices. There's a Google Earth Engine package, but with the ones that we're interested in at the moment is the Julia one, and that's the one we're going to investigate a little bit now. So for the first part, we will see how we access these indices from the package, and then for the second part, we'll see how we compute them. So the accessing is displayed in this diagram here. And so through the use of some offline functions, the spectral indices.jl reads the list from the original GitHub repository of the awesome spectral indices. It saves the JSON file, and from that JSON file, you can build all the functions that are expressed as strings into the JSON file as actual native Julia functions. And this is also useful when you are creating your own spectral index for your own research purposes. You can just define the index in a like a Julia struct. You can see here on the right side, I think, yeah. And you can define your index of your choosing, and the properties will be transferred through the use of function into the JSON file, and then you can also create the computing function from your own spectral index. And then if you want, you can contribute as well to awesome spectral indices by opening a pull request with a Julia code that actually creates the index and adding that to the list of the indices. And I have an example here, and I have made a bad choice of using the handheld microphone. Can I use this one? Test. Okay, thank you. Sorry. So just to have a quick example of so how this works. When you import the library, you have all the indices that are imported already into the namespace, so you can just call them, and you see the main properties of an indices there. This is an example with the NDVI. This is an example with the AVI. I will try not to do any live coding. You can see different properties here, and you can see what bands or parameters are used, like all the properties you've seen in the JSON file, and everything is at your fingertips on the Julia REPL, so that's quite instantaneous. And it's also very convenient. For example, when I was writing a paper, I was using, I think, between 16 and 20 different spectral indices, and having the DOI there was quite useful and handy to have it just on the REPL. But more importantly, we actually want to compute spectral indices, and you can do that to a handy function that's called compute index, strangely enough. And you can pass the compute index. There are different variations of this function, and the most important thing is that you can use almost any data type you want as parameters. So you could use arrays, name tuples, data frame, YX arrays, dictionary of any of the above, and more. So you have a very flexible way of actually computing and accessing these indices with a lot of the different data types. And from this, you can also actually use compute index using a string with the name of the index itself. This was created initially to have some feature parity with the Python package. I much prefer having compute index with the actual spectral index since it's struct, since it's important in the namespace. But you can also use it as a string if you're coming from the Python package. Or you can give the bands that you want to compute that are needed for the computation of the spectral index. You can give them as keyword arguments, and again you can manipulate all this stuff and also have the string and giving the argument as keyword arguments. Yeah. So just a quick VS Code example to showcase this. Here we have two values for the neo-infrared and red, and we will use a dict and show that okay, well, we have the computation of the spectral index as fed as a string. Computation of the spectral index. I should have tried this before, of course. Okay, well, I should have tried this before. Let's ignore this for the moment. But you can also have computation of multiple spectral indices. So in this example, we have, for example, the NDVI and the SFVI, and we provide the needed bands, and we compute them 3 at a time, as many spectral indices you want. provided you also give the necessary bands. And all in all, these packages is supposed to give an easy and fast access to a large list of spectral indices, and useful for speed up in your pipeline and computational tools. And the future directions is to add more data types for the input data. As you saw, I just have data frames, wax rays for like external packages at the moment, but I'm working on adding rasters and also tables.jl. And that is all. The QR code will bring you to the GitHub repository.
Yeah, thanks, Francesco.
Thank you.
Let's have just one question. Okay. And then we'll move to the next speaker.
Yeah, so when you define the spectral indices, you say near infrared. Does it contain a definition of like what near infrared is? Or do I have to choose myself like, this wavelength is close enough to what the spectrum was originally defined for?
So you can have it as a reference here. Usually the papers that create the spectral indices will give you some platforms on which they base their definitions on. So you can look at that and see, okay, well, for example, the NDVI has been tested on these wavelengths, so it should work for this. But yeah.
Okay. But I mean, some of them sometimes have more near-infrared channels. So.
Yeah, it's more nuanced than this, of course. But the point, if you're using spectral indices that are out there, of course, you have to reference the paper and first and see if what you want to do is in line with how they proposed it, for example.
Thank you.
Okay. Thank you.
Yeah, let's give it up for Francesca. Almost. Great. The next speaker we have is Nathaniel. He'll be giving, it's going to be a longer presentation. It's about fast probabilistic inference for ODEs. Okay, let's give a warm welcome for Nathaniel, and yeah, good luck, man.
All right. Okay. I hope you hear me. Yeah, thanks everyone for being here. Yeah, at any point in time, feel free to, or in the beginning, maybe reevaluate where you're sitting. I realized I was in the back for the last talks, and I couldn't see the slides very well. So feel free to just get up now and move to the front. So I'm Nathaniel. I'm a PhD student at the University of Tübingen. I'm basically at the end of my PhD, so I'm handing in next month, hopefully. And in my PhD, I worked on probabilistic numerics for differential equations. And well, in the first months, even when I started getting to know these methods and implementing them, I implemented them in Julia and found that to be very pleasant and worked on this library since 2020, I guess now. So I'm very happy to finally be able to present it here at the JuliaCon. Maybe before I start, just to get an idea of who the people are in the crowd. So does anyone use differential equation solvers regularly? Okay, that's almost everyone. Amazing. Who knows what a Gaussian process is? Okay, it's the same people. And who knows what a Kalman filter is? All right, okay. I think I can skip many of the slides. So we do probabilistic, or maybe who knows what probabilistic numerics is? Okay, it's still quite a lot of people, but half the people. Okay, so I will introduce probabilistic numerics and motivate probabilistic numerics by first talking about ordinary differential equations and how we typically solve them, and then point out what specifically the thing is that we try to do in probabilistic numerics. So when we have ordinary differential equations, so an equation like this in math, I've seen that this talk is tagged as math, so I'm allowed to put formulas. So we describe the derivative of some unknown function y with some equation, y dot equals f of y. F is called the vector field, so by evaluating f, we get information about the derivative of y. And if we also have an initial value, then this typically describes one function. There's one true solution to the ODE, and the goal, vaguely speaking, is just to find it. Visually, if we have, well, a very simple example, a logistic ODE, that means we have the blue dot, we have the arrows in the back, we want to find the black line. because if we follow the arrows, then there's only one black line that comes out. And now in the logistic ODE, that's easy to do. We can just solve it in closed form by hand. But when we have a numerical, or when we have more complicated ODEs, we cannot do that anymore, so we use a numerical method. And most of them operate, at least for ODEs, they operate in a very similar way. So first of all, instead of describing y, I describe y hat, because this is now an approximation. And then we also discretize time. So they are typically some recursive description of how to go from one point in time, y hat at t, to a future point in time with some step size h. And here, in the case of the forward Euler method, well, we just extrapolate along the gradient. Backward Euler makes the whole thing a little bit more complicated because it's implicit, so you use an additional numerical method on top. Runge-Kutta and multi-step methods do something a bit more complicated because they extrapolate in a smarter way. But in the end, they all describe a y hat, they all discretize time in some way, and they all evaluate the vector field in order to construct this solution. And while they give you a y hat, it's still a reasonable or a meaningful output in the sense that in the limit, where if you make the step size small, you get the true solution. So the smaller the step size, the closer the red line is to the black line, so that is good. But at the same time, the red line is never actually the black line. So even if you make, for any finite step size, there will always be a difference. And you can see it for large steps, you can see it directly. For small steps, you might not see it, but there's still some numerical error. So in some sense, this initial task of finding y, you failed because the red line is not the black line. So if you put all your belief into the red line, then this is not actually the system that you're solving. And so that's where this probabilistic interpretation starts. So there is some unknown function y that we try to estimate. So this is an estimation problem. And we use information to estimate it, which is this vector field evaluation that we do along the way. And so in probabilistic numerics, what we do is we write it down as an estimation problem. We treat it as an estimation problem in a Bayesian way. And so in the end, we get belief over what we think y of t is in a probabilistic way. Because, I mean, it could be many different things because there is some error, but we get, well, a probabilistic description of what we think it is. So we treat ODE solving as the Bayesian state estimation problem that it really is. At least that's what I would like to motivate. And so one quantity to look at is, I would argue, is this one. Because it now describes the thing that we actually try to compute when we use a numerical method. Before that, I had the mathematical description and this mathematical ideal object that we would like to have. This is a bit more practical because we might be able to compute that. So we want a belief over y of t such that it satisfies the initial value and it should satisfy the ODE, but we're fine if the ODE is only satisfied on a discrete set of points. If you take infinitely many points, then this object should be similar to the object that we described before, but infinitely many data points is something that's hard to work with in the same way as solving an ODE exactly is hard to do. So how does this object look? Before I explain to you how to get it. So this describes the probability distribution of a y. So assuming we have it, I can sample from it and plot samples. So I did. These are the samples. They're just so close together because the numerical error is small in this case, because logistic ODE is trivial, that you cannot see the individual green lines anymore. But if I plot the individual green lines in the space of y dot minus f of y, then I see that they look like this, and this gives you an idea of what's happening. So I conditioned this process on the fact that on a discrete set of points, this residual should be equal to 0. In between the points, who knows? And this who knows is basically, well, whatever probabilistic model you choose. That's what we do in Bayesian inference. So to get this, I chose some model, conditioned it on these zeros. In between, there's something happening according to my prior, and then this is the posterior in solution space. Okay, so very briefly, what kind of models are we using? So we use Gaussian processes. We actually use Gauss Markov processes. I don't know how familiar you are with this topic, but if you know Gaussian processes, the standard thing that always comes up is they are cubic in the number of data points and expensive and so on. Our input is time, and so if we also put the Markov property in a GP, then it turns out inference is fast and exact. Then to do Bayesian inference, so we need a prior, we need a likelihood, and we need an inference algorithm. The likelihood is basically whatever is to the right of this bar, so that's the stuff that we want to condition on, which in our case is not even some noisy observation, it's just an equality constraint. So it's a bit of a stretch to call it an observation model, but that's how you implement it. We also often call it an information operator because it's kind of this virtual self-made data, I would say. So it's rather information that we impose. And well, you can see that this equation is here. We just put everything to one side and say it's equal to 0. And this also is equal to 0. So the left side depends on y, the right side does not. So the right side is the data point and the left side is the measurement model. Same for here. And then if you take these two things together, what you have is, so you have a continuous model that describes some state. You have a discrete observation model on the data points, well, on the times that we chose. So this problem in filtering and smoothing is known as a continuous discrete state estimation problem. I can strongly recommend, well, there are books by Simo Serke, I think, is quite well known, on Bayesian filtering and smoothing and many things on this topic. But, well, you can solve this, vaguely speaking, with Bayesian filtering and smoothing and any algorithm that you find in there, which is, well, the extended Kalman filter is what we use mostly. If the ODE were linear, it's just a Kalman filter. You can use uncentered filters and so on. And so, well, to describe this visually again, so the priors typically look like this. It's super uninformed. It's an integrated Wiener process prior. If I take each of these green lines, I can squash them again through this residual function, and then it looks like chaos. And then once I do inference, I condition all of these orange lines onto the blue dots. And by doing that, the green lines collapse onto the ODE solution. And the magic to get from one to the other is extended Kalman filtering. Yeah, maybe just briefly, this is pseudocode on how this ODE solver looks. I did not introduce these symbols. Those are basically the prior. But here's the ODE and here's the time discretization. And just to give you an idea of what algorithmically happens, there's also, again, some loop that lets you go from left to right in the ODE. And then if you ever implemented a filter, there's typically a predict step and an update step, and you just iterate both. You predict, you update, you predict, you update. This code is actually very close to what you can implement in Julia in order to get something that solves ODEs. If you're curious about it, I have a URL here. You can find it on my GitHub, where I gave a 90-minute tutorial in Julia to people that do not know Julia, and still in 90 minutes they were able to implement basically this to solve ODEs. So to get a working example is really, really, really doable. So if you're curious, I would encourage you to, well, if you're curious about learning about the method, I would encourage you to implement it yourself. Of course, for using, there's the package. Maybe this works. Videos get more complicated. But then if you look at what happens, then again, the ODE solver solves the whole thing from left to right the same way as you would, as your standard Runge-Kutta method does. So it is algorithmically really similar to solvers that you know. And at each step, there's this extrapolation happening and then an update happening. But since we have a probabilistic model, we can also extrapolate into the future, which is what I've shown here. So everything that happens towards the right is basically according to the prior given the current state. All right, and so what do you get when you do this? This is, I think, from the README of the package. So when you solve an ODE with these methods, and I will show to you how, then, this is a Fitsu-Nagumo ODE, I think, just one of these standard problems. Then you get your standard ODE solution, U of t, it's typically called in the SciML context. But then inside this object, there's also uncertainty estimates that describe the numerical uncertainty of the solution that you can just access, because each of these things is basically a Gaussian, so you can plot the standard deviation, and you see that numerical error spikes roughly in these areas where the orange line is steep. That's when the orange error spikes, and it decreases again afterwards. Maybe this is an interesting thing to look at, because if you come from numerical analysis and you think about numerical error, often people think about worst case error and this idea that error always accumulates and so on, but that's not actually the case. So imagine if you have an exponential decay ODE, the numerical error goes to 0 because the solution just decays. So numerical error can go down, and it does. So this error is the thing that the method believes the error is that itself actually made. So it's a different object than this worst case exponential error. And I would argue it's more useful because it's what's actually happening. Okay, I have one slide for the skeptics, I would say. So I quickly explained this this method that is an OD solver that maybe, well, at least half the people here don't know. So is this actually an OD solver? And yes, so people in the group that I did my PhD in and other groups in the UK, for example, worked on these methods and have shown that these are actually OD solvers because they have convergence rates. So I think this is maybe the biggest checkbox that you need to satisfy. If you make the step sizes small, the mean converges to the true solution and the uncertainty converges to 0. So eventually it does the correct thing. So this is very important. Then if you care about stability, you can look at stability of these methods. These are astable or they're L-stable versions. There's a connection to classic ODE solvers, if you know about multi-step methods. Maybe one point to linger on a little bit is how complex are these methods from a theoretical perspective. So since we use filtering and smoothing, they are linear in the number of time points. So not the bad GP case, but actually what you would expect from an OD solver, which is why it's not even written here. But if your ODE is d-dimensional, then it's either linear in the dimension or cubic in the dimension, depending on if you use a version that is semi-implicit or an explicit version, which is exactly what your standard Runge-Kutta method is also complexity-wise. So an implicit Runge-Kutta method is also cubic, which is why solving stiff implicit large dimensional stiff systems in large dimensions is non-trivial. We have the same problem, but also the same linear scaling. You can do step size adaptation. It's implemented in the package also. Yeah, we did a parallel in time version. I only talk about ODEs, but this idea also scales to higher order ODEs, DAEs. You can look at energy preservation. So these things also in the package. These are not, but could be. So BVPs are also a topic of interest, and PDEs with a method of lines. And you can use these methods for parameter inference. I have some plots in the end. Yeah, maybe one other place to point you to is there's a book written by my professor Philip Hennig and co-authors, which is a book about probabilistic numerics. So it covers probabilistic numerics for ODEs, but also for other numerical problems. So Bayesian quadrature, if you ever heard of it, or Bayesian optimization, also fall in this category of topics. So that's a good starting point also. Okay, so now about the actual Julia package. I'm more than halfway done, but now it only starts here. But the thing is that it's actually not very hard to use. So how do you use prognum difficultar.jl? Basically, this is how you use ordinary difficultar.jl. You define your vector fields, initial value, time span, some parameters, the OD problem, then you just solve it with some solver. And to use prognum difficultar.jl, you use a different solver. And then that is it. So the solution object is now not an ODE solution, but a probabilistic ODE solution. And it contains a bit more things. But in principle, this is what's happening. So that also means, so I really piggyback completely on ordinary difficultar.jl. That means that many things that work for ordinary difficultar.jl just work for prognum difficultar.jl out of the box. Which also means that I don't have to write too much documentation because they already write a lot of documentation. So the getting started place here is probably the thing that I would point people to how to use my package sometimes. And the whole description of all of these keyword arguments that I have and so on, many of them just work. But of course, I also have docs that explain, well, mostly the differences of what's in this probabilistic OD solution. maybe one fun fact also is in the SciML docs, you also find problemDiffQ.jl. It's listed under third-party uncertainty quantification. I would argue it's actually a solver, but then Taylor integration is also there, which are also doing solvers. So maybe that's the place. Also, if you Google for problemDiffQ.jl, you get to this homepage because SciML is better in search engine things. So what does the package contain? It contains, well, explicit and implicit solvers. EK0 is the explicit one. EK1, if you want to play around, is probably what you should use because it gives you nice uncertainties. You have different orders, as you would expect. You can use them by just putting the order in the brackets. You can make it quite large and it still works. So if you're interested in very high order ODE solvers, maybe that's something for you. You have, well, step size adaptation. We have dense output, so in between the points we get an interpolant, so not just a linear interpolation, because it is it is basically doing Gaussian process regression in some sense. So the object that we describe is a function, so we can evaluate it in between. This is also the output of a plot recipe, so that's nice. And you can solve, well, Hamiltonian problems and add some callbacks for energy conservation. So most of the callbacks should just work from differential equations.jl. But of course, it's your discretion that the callback does something useful. And if you do the standard manifold projection thing, that's a very non-probabilistic way of projecting to manifolds, so there's also a probabilistic version of it. And then, yeah, you can see numerical error. So here I made the tolerance levels high enough that we can see something. And so how to interpret this is the 95% credible interval, and we believe the true function is somewhere in here. We can also sample from this object. So these are all samples that could be the true ODE solution that we computed. We have different priors. We have likelihoods to do parameter inference. And yeah, and there are some things that are missing. So on the engineering side, something like we cannot support DAE problems right now because in ordinary difficulty, either you're an ODE solver or a DAE solver. We are both, but that doesn't work right now. And then maybe one bigger topic is adjoint sensitivities. That's just an open research problem. So how do you how do you compute these things from a probabilistic numerics perspective? So yes, someone should write a paper about this. And then, yeah, I said we can use other filtering algorithms. They're not implemented. Would be cool. And yeah, a few more interface things. So just maybe 2 more things. When we talk about probabilistic, well, in ODEs, well, in the SciML thing especially, there's always this question about methods needing to be super, super fast. And then on the other hand, when you look at probabilistic inference, then often maybe the doubt is that isn't it slow to be probabilistic about something? And I already talked about complexities earlier, so on paper, not. In practice, it depends. So here I just solve a Lotka-Volterra ODE, so it's low-dimensional and non-stiff. And if I compare myself to these super optimized ordinary difficulty solvers, then there's a factor of 100. On stiff ODEs, it's more like a factor of 10 for this specific one. Again, it's benchmarks, so it might depend on the problem. But then again, a factor of 10 is not too bad, I think, because we also, so in these methods, we compute strictly more, right? So instead of computing a vector for each location, we compute a vector and a covariance matrix. And this numerical uncertainty. And so if you wanted to get the numerical uncertainty in some other way, probably you would need to do more work. So I'm not surprised that the line's above, it's just a matter of how far above. And then there are also some examples where they're pretty similar. So for a second order ODE that is like 40 or 30 dimensional roughly, it's pretty close together. So I would say that there's the potential to be quite comparable and very useful for these problems. Maybe one last pointer. I only motivated the whole thing with numerical uncertainty. There's a bit more than numerical uncertainty that you can do with this. And so we had 2 papers on ODE, well, probabilistic numerics for ODE parameter inference that I would love to point you to. So in parameter inference, we want to find the parameters of an ODE such that it explains data. And maybe the one thing, like the one very clear example is if you have an oscillator and you start out of phase, then typically your standard least squares approach converges to a local optimum that looks like this. which is why people do multiple shooting and like many different things. And one of the things in this list of things that you could do is probabilistic numerics, maybe, because if you get if you see that it's a bad explanation, you can get uncertain about the ODE solution. And when you're uncertain about the ODE solution, what you end up doing is interpolating the data, because we solved the whole thing as a filtering problem. And if you just let the optimizer run, eventually you get to this output. So that was pretty motivating. We did that, well, this is presented in 2 weeks at ICML by a colleague, where we did that for a more interesting problem than an oscillator, so these Hodgkin-Huxley ODEs. And here's the explanation why. It's in the docs. Yeah. So, yeah, the summary is ODE solving a state estimation, and you can actually solve it as a state estimation problem. Try it out, and yeah, please try it out. I would love to hear from you how it goes. Send me a message on Slack, open issues. Yeah, I also need a logo if you've seen it. So if you're excited about this, I'm very much looking forward to talking to you. Thanks.
Thanks. That was awesome presentation. Yeah, thanks a lot. I guess there will be quite some questions in the audience. Anyone? Okay. So I'll start from there.
Thanks for the great talk. You mentioned the in the last part the inverse problems, and I'm working on inverse problems. What I do if I want to tackle the inverse problem probabilistically, I would use a probabilistic inversion like Monte Carlo or Hamiltonian Monte Carlo. What is the advantage of tackling the forward problem probabilistically to do the inversion from the get-go instead of just using a deterministic approach for the forward and then do the inversion probabilistically?
Could you expand a little bit on what you mean with doing the inversion probabilistically? So do you care probabilistic in the sense of you care about posteriors over the parameters, or
yeah.
In which sense probabilistic?
I solving the ODE or the PDE with the solver, so with a deterministic solver, and then combining your data to get the model parameters, but probabilistically. So that's what I mean.
Okay, yeah, that's a good question. I think that's one of these details that are often tough to communicate in probabilistic numerics. So there are many different things that you can be probabilistic about. Here we compute maximum likelihood estimates for the parameters, so a point estimate of the parameter. But that's basically because in this paper, so to get this, we need to define a likelihood of the data. I think for anything that you want to do, is it the maximum likelihood estimate, a map, or sampling from the posterior, you need a likelihood term to evaluate. And so the likelihood term can either be based on doing least squares with Runge-Kutta, or using Runge-Kutta and then just computing the mean square error for each individual location, or it can be a likelihood term that is aware of the numerical error, or that is a probabilistic model. So it's orthogonal. You can use this also for MCMC.
Okay. Thank you. Next question.
Thank you for your talk. I assume you have some form of large deviation estimates. I'm curious how these compare to the sort of deterministic sort of worst case error bounds and error orders that one gets.
I'm not sure what you mean with large deviation estimates.
So like probabilities that it is such and such far away from the true ODE solution.
Yeah, what we get out is basically a Gaussian process posterior. So that describes our belief over where we think the true solution is. And then the difference of that to worst case error bounds, I think, is that, well, the worst case error bounds assumes that, or from my understanding, typically that's a very theoretical mathematical object that people look at to prove that solvers converge. But normally when you have an ODE, it goes like this. So very quickly the error could be anywhere, but then you hope that if you make step sizes small, it still goes small. But this is probably a very bad estimate of something that is here. So in probabilistic numerics, we try to quantify the actual numerical error. So it's more of a, yeah, in this specific case error. Does that answer the question?
Yep, we have just 1 minute for another question, and then
I would love to
you can reconvene.
After,
after the talk. Yeah.
Okay, so my question is just quickly considering slide 15. There was a plot where I didn't understand why Yeah, exactly here. So we have these data points, and this is where we evaluate the ODE. Um, oh no, okay, it makes sense. Yes, sorry.
Yeah, so the dots here are to show the step sizes that the solver took, and in between it's interpolation. Yep.
Yeah, thanks a lot, Neil. I think,
you.
yeah, it was, let's give a big round of applause for this stellar work. Awesome. Yeah, I guess, yeah, there will be a bunch of people asking you questions right after. So, yeah, don't hesitate to just catch him in the aisles. So, yeah. We have our next speaker, Raphael. If, yeah, they're here, I hope. And they will be talking about geointerface.gel. Okay, you're here. Awesome. Two speakers. Okay, let's welcome the speakers.
Test. Oh, hello. Thank you. It is on. Okay. Welcome to What's New with GeoInterface, Traits for Interoperability. I'm Maarten Pronk, and this is Rafael Schouten. Or Schouten, oh, I should say. Here we're in Holland, so it's Schouten. Okay, so why GeoInterface, right? So you go back to the question of, very simple, what is a point? Everyone likes to define points in their packages. So a point would be a vector of a few floats. It could be a tuple of a few floats. It could be a tuple with also, let's say, a third dimension, which probably would be the height. Some people don't like vectors because they're too slow and implement static arrays. Then people like some more explicit stuff, and they make a name tuple with a x and a y, or maybe some other names. If you reverse the tuple, then you have a different type, and again, it's something different. And then you can also implement structs, and well, basically you can go pretty nuts already with just defining a point in your ecosystem, in your package. And if you move on to line strings and polygons and other complex geometries, it becomes even harder to define really what a point is. So hence, a long time ago, I think Martijn Visser, I just saw him here, and Yeezian made a GeoInterface package to basically standardize what is geometry in the Julia ecosystem. And this is based on the simple feature standard, and we talked before about this all the way back in 2019, 20, and 22 at JuliaCon, I believe. And that previous GeoInterface was basically based on supertypes. So people were expected to, if you implement GeoInterface to standardize geometries, you implement from an abstract point or abstract multipolygon. And of course, that only works if you can actually subtype. If you're already subtyping abstract array, you cannot implement this spec. And so we came to a 1.0 design, and for that I will hand over to Rafael.
So at that point, there are a lot of geometry packages in the ecosystem, like geometry basics that already subtyped array and had that we couldn't get to subtype our type, geointerface type. So the idea was to rewrite the package with a traits-based system. And there are a bunch of attempts at this. I think there was about 2 years of this rewrite. Actually, Martijn Visser, I think, started that. Did you? Yeezian started it, but it was over a long time, and finally we finished it a year and a half ago. And the idea of using traits, like the reason for using traits is that packages can implement the interface without inheritance changes. So geometry basics can implement the interface and does, and a lot of other packages. So we don't have to argue about who has the dominant type or force any changes in the ecosystem. Geometries can be abstract arrays if they want, and a really good side effect is we get no copy interop for free. So in R and Python, it's a really big deal to get no copy interop, and they use arrow and things, where we get that for free because of the traits interface and packages reading all types. Okay, so what the interface looks like now is this set of methods that you need to implement. So here for this custom point, we have to implement isGeometry on the type. Is this kind of thing a geometry? We have to give it a trait. This thing is a point, so we have a point trait. And then we need to define methods like the number of coordinates in the point, getting one of the coordinates out by index, and a bunch of other methods. It's quite a complicated interface, actually. We have the same kind of thing for polygons, same start, but here we define ngeom and getGeom, so we're getting the geometries out of a polygon. And those will be line strings or linear rings, which will again have to implement this interface. So we have this nested getters. We have other methods like geointerface.crs, geointerface.extent, that will get CRS data and extent data if it exists in the object. Of course, not all geometry types implement these. They're really geospatial things. We have a bunch of other methods like area that kind of not working so well, but we'll talk about that later. Currently, we have 41 implementations of this interface, so it's pretty widely used now. There's common sources, Geometry Basics, ArchGDAL, libgeos, Shapefile, GeoJSON, one-end geometry, and KML. And there's a bunch of consumers. We can't fit them all on the screen. So that's about 30 packages that will consume all of these geometry types. And none of the consumers need to depend on the sources, is the idea. They don't know anything about the source geometry types, but they will accept them. And then we have 850 indirect. Mostly that's through Geometry Basics and other geometry packages. Not people directly using GeoInterface. So things that work great at the moment is this object accessor interface really works. So GeoInterface can convert between most ecosystem geometries. This single, you can just convert to ArchGDAL, convert to Geometry Basics. Consumer packages like Geometry Ops and rasters accept most geometries, so you can rasterize libgeos or a shapefile and that will just work. You can use them in Geometry Ops methods. And packages like GeoJSON, GeoDataFrames, and Shapefile will write any kind of geometry. So you can just call, you can see here we have a really simple geometry, just a point in a data frame, and the same command, GeoJSON.write, GeoDataFrames.write, Shapefile.write, will write a file from any kind of geometry. There are still things that could be better, of course. The predicates and functions don't really work at the moment. We don't have a way of dispatching on a lot of the types, and we haven't decided what kind of blessed standard package to use. We're very hesitant to go down a plots or Mackie style of interface where you have a default backend and a loading method. So some of those methods don't work that well. Yeah, plotting kind of works, but there are a few things like we have to use, like using GeoInterface Mackie to get plots of some geometry types to work. The documentation and discoverability is really bad, and that's the thing about having this ecosystem-wide interface, is that it's hard for people to know what is doing, where are things happening, what package do I make an issue to, what documentation do I read. So we need some integrated docs. And there are a bunch of plotting and conversion things that aren't fully implemented for features and feature collections. Okay, so our future plans are implementing CRS traits. We're really keen to have projected in geographic traits, so coordinates in meters and coordinates in latitude and longitude. If you do something like area or length on those objects, it will be done correctly, spatially, instead of always being done in meters, which is kind of the default. And happens in Python and other ecosystems a bit as well, but we're pretty bad at that. We want to implement raster traits, so we know when an object is a raster and it should have extent and CRS traits. These are all open pull requests. And this having default implementation backends work, and we've got a bunch of design issues to resolve there. Ansha wanted me to plug this Julia Geo tutorials, and hopefully this is going to turn into some kind of across the ecosystem documentation that will start to pull these GeoInterface things together. Yeah, that's it. Thanks a lot. And any questions?
Thank you. We have time for, first of all, applause. Yeah. We have time for one question. Anyone in the back of the room, maybe? No. Okay. Yeah. This rocks.
You're welcome.
Cool.
Thanks.
Cheers.
Yeah. Okay. Then I guess in the interest of time, we will move to the next speaker. I see, quite some people came to find help how to write allocation-free Julia code. So, thanks a lot. Again, for our speakers. Gabriel, okay. Okay, just people at the back, there's quite some seats in the front, so just come closer. Okay, let's welcome our speakers, first of all. Yeah. All right, let's go.
How about now? Oh, okay. All right. We okay? All right. I'm Cody Tapscott. We're here with Julia Hub. We've been thinking a lot over the last year about how to bring Julia to new systems and new places that it usually hasn't been deployed to before. AlloCheck is just one piece of that story, but we're really excited to talk to you guys about it. So I think I'll pass it over to Gabriel here to talk more about the problem we're solving here.
Okay. Hey, I'm Gabriel, and let's dig into it. So what is AlloCheck trying to solve? Basically, I think if you've written Julia before, if you write allocation-free code, reduce your allocations is a thing that gets drilled down into you a lot. And it's sometimes annoying to figure out things like what is my code allocating? Where in my code are allocations happening? Am I covered? Like, I eliminated the allocations in part of my code, but maybe there's a corner case that actually allocates. How do I make sure that I made my code allocation free, but it can regress? And I think the cool thing that I think Cody touched in, like, can I disable the GC because I have a control loop that cannot be paused? So to disable the GC, you need to be sure that you're not actually allocating anything. And to exemplify that, I have a little function here that just allocates some arrays and tries to build a histogram. I think Christopher yesterday made a similar thing. And you can see here that this function, each execution does 20,000 allocations, spends time in GC and whatnot. And we want to avoid that. So you have a couple tools you can use, for example, the allocation profiler. This is the pprof visualizer for it. You can see it's not super easy to understand what's going on there. There's a bunch of things. And if you dig into it, you're going to find what's happening there. And it is very useful and should be used together with AlloCheck. But we think that AlloCheck is a nice place to start because it gives you something that looks a lot like a Julia error. So you can see here, for example, it shows that you have an allocation of a vectors in 64. It gives you a stack trace, very much like a Julia error. So I think everyone's a bit used to seeing how these work. And we have a couple errors. I think Cody can go a little bit deeper.
Yeah, great. Okay. So these are the three kinds of errors you have to worry about when you're working with AlloCheck. The basic idea here is that you're going to be using AlloCheck when you have code that you're pretty sure you should be able to completely eliminate the allocations from, or nearly completely eliminate your allocations. And in order to do that, you're going to have to solve a couple of the other problems as well that are also part of good hygiene in the case you're able to get this kind of highly efficient dynamic dispatch free code. So the three kinds of errors here. First of all, the problem we're interested in, of course, are these allocations. That's what inspired us to write this package to begin with. And these, in the most conspicuous form, are these kinds of things where you're creating a mutable struct or allocating a vector, or maybe you're just accidentally in some branch of your code, you have a cache that you're using, but there's a chance you might resize the vector inside that cache. That's a possible allocation that we need to consider too. So we cover that case as well. But in order to get there, there are other corner cases we also had to consider. So there's stuff here that might look fairly innocent, like just a type assert for an integer check. That might end up calling into subtype, a function in the runtime here. And that inside actually uses malloc. So even though it doesn't allocate any Julia objects, it's still a problem for the extreme case that you're trying to run this in a hot loop with the GC disabled. We have to make sure we call that out for you as a possible allocation. The nice thing is that allocheck will tell you, oh, this is an allocating runtime call rather than an allocation of a typical Julia object. So you can say, okay, the problem here is that I'm calling subtype. That's probably related to the type assertion here, and then you can kind of figure out how you can get around that issue. And to be clear, not every type assertion is a problem, but type assertions with poorly typed arguments often are. So if X here happens to be inferred as any, then this can end up as a runtime call. Whereas if X is concrete, usually the compiler will just figure out that that's always true, and you've got no issue here. And then finally, dynamic dispatch. I think everyone who works with Julia is kind of familiar with this as a concept. But allocheck makes this kind of like a first-class concern, because if you've got a dynamic dispatch, the problem here is that we don't know where these function calls go. And I can't make any guarantees about code that I don't know is going to run or not, or where it comes from. So first place requirement in order to be able to guarantee that your code is going to be allocation free is that we have to be able to make it sufficiently type stable that all dynamic dispatch is gone. So you'll also see in the output from allocheck, you'll see errors that say, this is a dynamic dispatch. We don't know whether the other side of that dispatch allocates or not, and so we're going to have to flag it to you as an error anyway. All right. And then with all that in mind, I think we can go back to our example here, and Gabriel can talk about how you're actually going to fix it now.
Right. So I think there are multiple ways of fixing allocation examples. Here I took a very simple approach. We had that example. We can see here that we're allocating an array on each loop iteration, and I think the first two people will say, oh, well, pre-allocate, and that's what we did. So I made a histogram fast. It just takes in a scratch buffer that would be reused across calls. So you paid this allocation cost once at the beginning of your program, and we can see that this function now has one allocation, which is the return of the function that we could also potentially save, but that's instead of 20,000, one is a lot simpler. The GC isn't stressed about it. And yeah, that's a simple thing one can do, and allocheck would help you to do it. So for example, this error would go away in allocheck. And yeah.
Yeah, so I think the key thing to take away from that example too is that this case is pretty clear. I think probably all of us have had an experience where we have some Julia code that looks like this. We stare at it for a little while and we see the allocations and lift them up. This is easy, but the idea is that allocheck can help this even if it's hidden in some library you're calling in, or if it's hidden in some if check that is hit in some test case that you didn't happen to cover. So we provide this kind of reasoning, but for more complex code that you might not be directly staring at. And so now, with that in mind, with the basic use case, we'll get into some of the more complexity here. One thing to keep in mind of, which allocheck doesn't yet help you very much with, is that there are really two types of allocations. I think people often have an experience with the allocation profiler where you look at the results and you say, okay, it points to this line. There's no allocation there. What are you talking about? But there is an allocation there. I mean, we are allocating, but you didn't write the allocation. You didn't create any struct. You didn't create any vector. You didn't resize anything. So the question is, where did that come from? That's what we're trying to kind of explain here. Because Julia is a high-level dynamic language, it gets to make decisions about, for example, whether a tuple is going to live on the stack or on the heap. And whenever it first puts something on the stack and then decides, oh, actually, the situation has changed, and all of a sudden this object needs to be moved to the heap, that becomes a late, like a deferred allocation of that object. So that's what is happening here, for example. We have a tuple that normally could live on the stack, but because you put it inside a poorly typed field of a mutable struct, then all of a sudden we need to move this to the heap. And so that tuple gets copied to the heap in this code example. There are a couple different ways to fix this. First of all, you could use mutable types to begin with and make sure it starts on the heap and stays on the heap. The other way to fix this is you could make sure that that field is sufficiently well typed that we can just say, oh, that's a tuple of int. I know exactly how large that is going to be, and I'll just reserve some space inside that struct. I don't need a separate pointer to it. So there's no copy that needs to happen. But that's some of the extra complexity that you can get into here in terms of copies that can be kind of invisibly inserted by the runtime. So this is something to watch out for. We have some ideas about how to improve this, but we'll come back to that later. And then Gabriel here is going to talk about some other common pitfalls in terms of the kinds of issues people usually run into in their code.
Yeah, so like using allocheck, we've found there are typical cases where you can get some allocations. One of them is simply you make an extra copy or a struct that maybe you could have been immutable struct, you made it mutable for ease of use, and now you have allocations in your code that are unnecessary. alloc has a couple, it's not exactly a false positive, but it's a really rare positive. So broadcasting has a check that if you alias the arrays you pass into broadcast, it has to make a copy, but that's not common. But alloc will flag, hey, by the way, you can have an allocation here, and you run time or the allocation profiler, and you don't have an allocation. And we have some ideas that maybe we could try to identify those, but in essence, even if it's in a corner case, alloc will flag it. And an optimization that's interesting is that Julia can initialize an allocation, but if you have an implicit return to your function, like in the example there, because you're returning the object, we have to allocate it. So be aware that maybe you put a return nothing there, and then the optimizer is able to remove that allocation. Yep.
Great. And then to close, we just wanted to mention that we're happy to say that we just updated this for Julia 1.11. So you're ready to try this out on the latest RC if you'd like. And then in the future, the main thing that we'd like to fix is what we talked about in terms of these runtime inserted allocations. We want to give you a hint about why they're there and separate them from the ones that you wrote explicitly in your own code. So yeah, thank you very much.
Yeah, I imagine there will be quite some questions. So given that it's the last session, we'll have 3 questions, no more, but I believe that you can catch Cody and Gabriel right after the session,
Yes.
right?
Yeah.
Okay, so first question. Yeah, I see the hand there.
Thanks. Really cool tool. What are your thoughts on LSB and static analyzer or linter integrations?
So I think alloc maybe could be used on it, but it's probably not the right tool because alloc works at a very low level. So if we believe it's more of a testing tool, that's something to inform your code in your IDE. I think there's 2 talks that are going to happen in the afternoon that work at a higher level. Basically, it's difficult to translate whatever alloc finds to something in Julia. Sometimes it's easy, but usually you've seen those cases where you're putting a tuple into a immutable thing. And I don't think we can really get that information back to an IDE into an LSP protocol like JET or something built on top of like a Julia level static analysis would be able to do.
Yeah, I think the biggest challenge that jumps out to me is that alloc needs to still have a decently well-typed entry point to your function. So you have either an explicit signature that you give it that you say, I want to check any subtype of this signature is going to have no allocations, or you go ahead and mark your function with @checkAlloc. We didn't show that here, but that means now, Julia naturally, if it does a dynamic dispatch into that function, it'll say, okay, you called this at runtime with int float32, int 8, something like that. And then for that specific specialization, it'll go ahead and check that that particular specialization is allocation free. Often that check is a lot more precise than something we can do if you just check integer, abstract float, for example.
Okay. More questions? Okay. One here.
Thanks for the talk. Very basic question, but how do I actually use alloc to check if my function allocates?
Yeah. There's 2 functionalities. They're both called checkAlloc. One is a macro that you put in front of your function, and it uses generated functions to make sure that that function doesn't allocate at runtime. And there is the code typed. I think we're based on code type. There's a macro version where you put your function in some arguments, and there is the non-macro version of it that you just put a function in a tuple with the type of the arguments. That also works. And both of them do basically the same thing. One just happens to do it when you call the function. The other is like a compile time check, if you might think about it that way. And both of them, if you're used to add code typed or add code warn type, the usage is exactly the same.
Yeah, the version of code typed is something we that kind of form where you put it on the call site is something we want to add, but it's not in there right yet. So that's one thing you might find missing. But other than that, the usage should be very similar to code typed, and you can also add it as a decorator on the function declaration.
Okay, that's going to be last question for this session.
Probably similar question. Is this something you put in your unit tests?
I'm sorry, can you repeat the question?
Is this something you would like to put in your unit test? For example, you've optimized it, and then you can put this check as a unit test to make sure it doesn't fall over?
The 2 cases that we considered kind of primarily here, Gabriel alluded to one, which is that you might have a long-running hot loop where you really need a hard guarantee about allocation freeness. In that case, that's really what the use case for this sort of @checkAlex function declaration was designed for. It guarantees you can't get into the code at all unless it's allocation free once you're inside, which means you're safe to turn off the GC, for example. The other use case, which I think a lot of users will use when they just kind of want to make sure they've got good hygiene, but they don't have hard requirements on like they don't need to avoid the GC for correctness. They just want to do it to have good performance characteristics. In that case, yeah, I think adding examples to your tests would be a very common case. Another case that we want to explore in the future would be the chance to mark your function as whoever ends up calling this function, whether it's in a test or it's in production code, enforce that it's allocation free. And with the extra caveat that, of course, it might throw an analysis failure error or something of that kind. But that's still exploratory.
To your question, I think SciML is using quite a few of allocheck unit tests basically to make sure that their solvers and other hood loops do not allocate. So that is a supported workflow, and I think one of the main workflows we aim to support.
Awesome. Yeah, with that, we're going to close the session. Thanks a lot for all the speakers and participants. Yeah. Yeah. Right.
You guys can catch us after.
going to be from Safer from EPFL in Lausanne. He's currently a PhD student in computer science, and he's going to tell us about how to use Julia to study this causal discovery.
Use this one, right? There we go. All right. Good afternoon, everyone. I'm Saper. I'm a PhD student at EPFL, and I'll be talking about recursive causal discovery with Julia. So first, I'm going to be talking about what causality is overall. Then I'll talk a bit about causal discovery, and then more specifically about recursive causal discovery, and then my package to do recursive causal discovery in Julia, and then finally I'll conclude the talk. So what is causality? To answer that question, I'm going to say what causality is not, and that is correlation. Causation is not correlation. And I'm sure many of you are familiar with this website, Spurious Correlations, that goes and finds two things that are correlated that have absolutely nothing to do with one another. So one of the examples that I found here is the distance between Saturn and the Sun correlates very strongly with an R² of, I think, 0.9 with Google searches for how to make a baby. And maybe there's something that I don't know, but I don't think those two things have anything to do with each other. So correlation, causation in general is not causation is not correlation. In fact, causality is the relationship between a cause and an effect. So something is causing some effect. So I have a little example here. It's we're looking at the income of an individual, and the income is an effect of their education level. So Y is an effect of X, and we see that little directed edge, so it's represented by the graph. It is also an effect of that person's parental socioeconomic status. And the parental socioeconomic status is also causing their education level, right? Because the parent chooses what school to put their children in. And of course, causality has many, research. It's used in many applications, right? Such as public health, education, or policy making. And in general, when we want to represent these causal relationships, we're using causal graphs. More specifically, we're using things called DAGs, so directed acyclic graphs. So the directed portion means that we have these directed edges. Acyclic means we have no cycles, and the graph is, well, we have a set of vertices and edges. So an example is like this. So x1 is causing x2 and x3, and we would say x3 and x2 are the effects of x1. And a key question that arises often in research is, what happens if we don't know the graph, right? So we know these variables exist, but we don't know the causal relationship between them. And we want to learn that through data, and that's where causal discovery comes in. Causal discovery, or sometimes also called learning Bayesian networks, is the process of inferring these causal relationships from data. And so, for example, we have some observational data, x1 through x5, based on the example that I showed previously, and you want to learn the relationships using this data. And a common approach is this algorithm called the PC algorithm. It was developed in the year 2000, and basically the way it works is it tests each pair of variables for their conditional independency. So basically it checks whether x is independent from y given some set z. And it does this for every single z essentially. And then if it turns out that x is independent from y, we know that there's no edge. So neither x is causing y nor y causing x. And then it does some orientation. These details don't matter. What matters is the learning portion, so learning the skeleton, is very, very slow. And it's slow because it has to test every single pair of variables. And in fact, it has an exponential complexity. So this is very, very bad if we have a lot of variables. And that's where recursive causality comes in. So recursive causal discovery. So in recursive causal discovery, the idea is to reduce the size of the graph at every iteration of the algorithm and then recursively learn the graph. So the way it works is we want to identify what we call a removable variable. And the definition for what a removable variable is technical, it doesn't matter. What is important is that a removable variable can be removed from the graph without affecting the graph too much, essentially. So we find a removable variable using these conditional independency tests. We learn its neighbors, and then we remove it from the graph, and then we repeat step one. So we keep finding removable variables, learning their neighbors, and removing them from the graph. And I have a little example here. So on the left, we have the variables that we're working with. On the right, we have the learned skeleton so far. And so we first identify x5 as removable using those CI tests. We learn its neighbors, so x3, x4. We remove it. We identify that x4 is now removable. We learn its neighbors, x1, remove it. x3 is connected to x2 and x1, remove it. We move on to x2. And then x2 is only connected to x1. And then once we only have one variable remaining, we're done. And so there are 4 of these recursive causal discovery algorithms. And I want to bring your attention to the number of CI tests that they're doing. Just the most important thing is PC, the algorithm that I said is the most common approach, needs an exponential number of tests. And these algorithms, under certain conditions, don't. The worst case is still exponential. But for certain structures, for certain side informations that come with the graph, these algorithms are going to perform much fewer number of CI tests. They're going to be much faster. And so we implemented recursive causal discovery in Python called RCD, and we implement all the 4 algorithms, and you can install it as such. But we don't care about that here, right? Because we're at JuliaCon, we care about the Julia implementation. And it just so happens that the Julia implementation is much faster than the one in Python. So we implemented in Julia. We look at the time it takes as a function of the number of variables of the graph, and we see that it's around 2 orders of magnitude faster. This is on the log plot. So it's, in fact, 150 times faster. And the way it works, of course, it's on the repository, so you can install it. And all you need to give it is a data matrix, right? So you can read it from CSV, or you can load the matrix some other way. You give it the data matrix and some CI tests. So here I'm using some Fisher Z test. It's for Gaussian random variables, but you can use your own custom test. You give the data matrix and the CI test, and then it returns you an undirected graph, which represents the skeleton of the causal graph. And if we compare it with this PC algorithm that I was talking about, we see that. So first, we're going to look at the F1 score. F1 score is essentially a combination of recall and precision. So the higher it is, the better the algorithm was able to learn the graph, right? So we see that RSL, it's one of the RCD algorithms in blue. Even by 200 variables, it's around 80%, right? 0.8 F1 score, whereas PC is lower at 0.6. And of course, in terms of the number of CI tests, it's PC is doing much more CI tests, so it's much slower compared with RSL. And as for future direction, we want to implement the other algorithms, because so far we only implemented RSL. There are 3 others. And then we want to add more CI tests. Right now, there's only Fisher Z test for Gaussians and Pearson partial correlation. And of course, we want to potentially integrate with causal inference JL. It's one of the popular causality packages in Julia. And with that, I conclude a bit of causal discovery.
Yeah, why would you say causal?
Because it's a causal graph, right?
Wouldn't it be a Bayesian graph, not a causal graph? Because every causal graph is a Bayesian graph, but not vice versa.
Bayesian networks don't give you the correct direction of the edge. So in Bayesian
Right.
networks you can also...
Oh, you mean in terms of that?
Exactly,
Yeah, I mean, so...
because you can't find both ways if it's a chain left to right.
Yeah, so technically, so I had this Meek rule step, right? Where is it? Yeah, here. So technically, you can learn some of the directions, right? So technically, in the end, what you get is a partially directed graph. So some of the edges, you know the directions of, some of them you don't. So in that sense, it's still, I mean, you're still trying to learn the causal graph. You just can't learn it fully. You can learn it up to an equivalence class, essentially.
And what are the problem sizes that you can kind of work with? Let's say an hour of compute.
An hour? I would say on the order of thousands, probably hour, yeah. Hour should be on the order of thousands, yeah.
Okay, one last question before we move on to the next talk.
Hi, sorry, maybe this is just like a different field, because so from physics, causal is like, time ordered, like what happens before, what happens after. How do you generate the synthetic data set, and like,
I guess, yeah, how would you, if causality is like the main as part of this, then it appears that the meek rules part should be the most important. So yeah, I was just curious as to how, like, because the CI tests are, well, that's correlation, not causation, right? Like classic thing. So
yeah. So I'll start with the second part of your question. So the meek rules part. So this part is not it's not doing any learning. So all the learning is done here. That's why I focused on learning the skeleton. That's the part that's actually dealing with the data and then using these conditional independency tests to determine whether an edge exists. The meek rules, it's just using certain assumptions that are placed on the graph, right? Because we know the underlying graph is causal, like we're making that assumption. There are assumptions on like the Markov property, faithfulness, so we're assuming those properties, and when you assume those, it turns out that you can orient some of the edges. So this is just like a deterministic algorithm that you go through and do. So there's no learning done here. And as for the first part of your question, so the general model in causality, it's structural causal model. So you assume if you have like, let's go to a graph. If I have something like this, I assume that x2 equals some function f2 of x1 plus some epsilon, where epsilon is some noise, right? And you don't know, well, either the noise or f. So that's where the causality comes from. So the children, so nodes are only dependent on their parents. So that's where the causality comes from. So in the simulations that I showed, the noise is Gaussian, and the functions I think I took linear functions, yeah, with changing coefficients, yeah.
All right, thank you.
Thank you.
Our next speaker is Patrick. 20 past, okay. All right, so then we have a 10 minutes break.
All right.
All right, let's continue the discussion during the break. I think we have some time after this talk. We'll have at least 10 minutes break again, so we can continue afterwards. So let's welcome our next speaker, Patrick. He's a PhD student at TU Delft, and his specialization is intersection between AI and economics. He's going to tell us about the trillion-dollar business using Julia.
Thank you. And sorry to interrupt the session. All right. Yeah, great to be here. Thanks again. So this is a very small package, actually, that really primarily just gives access to a data set that I have not compiled. So that's the big disclaimer here. This is a paper I came across that was published last year at, I think it was NACL or ACL, one of the big NLP conferences. And what these authors did is they essentially collected communications from the Federal Reserve in the US, so press conferences, speeches, and meeting minutes. And they built they went ahead and annotated these communications on a sentence-by-sentence basis and classified sentences as either hawkish, dovish, or neutral, which is central bank speech for do you want to typically raise interest rates, lower interest rates, or don't do anything. So this package just provides straightforward access to this data set. We cleaned the data a little bit, and it also does a little bit more, and I'll go on to explain that. So the context of this is that we have a paper coming up in 2 weeks at ICML where we argue that AI researchers should stop making unscientific AGI performance claims. This paper was triggered by a chart that I saw flying around on Twitter last year that showed how Llama 2 embeddings can be used to predict geographical locations of tokens. So if you feed the word London into Llama and you look at the resulting embeddings, then those can be used to predict the geographical coordinates of London. And we argue that this is not surprising at all because we know that models can distill meaningful information that predicts external data, and we have a bunch of examples in our paper. And one of the examples is using this data set that we provide access to here. So what does the package actually do? It provides very basic functionality for loading the preprocessed data, loading the model that is proposed in the paper, all in Julia. It also provides, and this is the little bit of extra, it provides basic tools for model inference. Essentially for the paper, for the experiments in our paper, we had to go ahead and compute model activations for all the sentences in the data set. So for each sentence, we essentially feed the sentence through the model and we store the layer by layer, last token activations. And those activations in the package are made available through artifacts. They're interesting because from an interpretability angle, we can look at these embeddings and at these activations and see if there's any interesting properties. So here's a little bit on the code. The functionality, the API is very straightforward. So you can use this simple function load all sentences to just load the actual sentence data with a bit of metadata on top of that. And then what the authors of the $1 trillion words paper also do is they link this data and later the embeddings to various external data sets of interest. So here we have some macroeconomic indicators, including inflation-related measures and interest rate-related measures. And the authors do actually provide all this data in a GitHub repo. Of course, it's all Python-based. It's also a little bit unorganized. No shame here, but we did a bit of cleaning, and the Julia version is now very, very organized, I think. So to load the model, we rely on transformers.jl. I've seen Peter run around here, so hats off to him here for this package. So that's loaded from Hugging Face, and we have a simple call here where all the keyword arguments that you would use with transformers.jl are still applicable. So you could, for example, load the model and ensure that the hidden state activations are still returned once you call the model. And here we go. This is actually what we also do in the paper. So basic model inference. You can use the sentences, then feed them, load the model, and then feed the sentences to this layer-wise activation function to get not the final output, not the final classification output, but to get the embeddings. So in case you're interested in mechanistic interpretability, this is useful. You don't have to do this from scratch anymore, at least for this data set, because we've already, as I mentioned earlier, saved all these activations for you as artifacts. So now you can just use this simple API call here, using the artifact string to get layers, activations for different layers. Now back to the story that I started with. So this chart that I saw flying around on Twitter, it was a very interesting visualization. So they showed, yeah, okay, these embeddings in Llama 2 are predictive of geographical locations. But then the conclusions, at least in the first version of the paper, they all hinted at, oh, we found evidence of AGI. This model is clearly sentient because there's a physical world map embedded in it. And we're skeptical. And to show this, as I said, we ran experiments with this much simpler model, to be fair. But here we have two sentences. One is clearly about inflation. The other one, so it is actually related to economics. The other one looks similar, but it is really about the deflation in the number of doves, I think. We have doves and hogs here. But yeah, essentially we made up sentences. This is clearly unrelated to economics, and you don't have to be an expert in economics to understand that this has no impact on inflation or any other economic measure if a central banker uses this communication. But when we actually go ahead and we apply the methodology that they use in the paper and we run linear probes on the embeddings, we tend to find that the predictions of that linear probe, they're the same. So that to us is like one very simple way to show that even though you might have predictive embeddings, so the embeddings might be able to predict, thank you, external variables, that does not necessarily point to actual economic understanding. And we run these probes for all the models, and we show, yeah, we find predictive performance, and that predictive performance is actually better than for baseline models. But if we feed the model junk, then we get the same. So we run essentially this small motivational example that I showed you. We run that multiple times, and we, yeah, as one of our experiments, show that clearly this cannot be seen as evidence for AGI. So the goals for this package, and with this I'll finish up, is, well, it provides a very basic functionality and access to this, what I think is an interesting data set. There's scope for increasing the scope of this package by adding more data sets. So any types of contributions, but also just simply using the package is very, very welcome. And with that, I'll open up to questions.
All right.
So I'm curious about, like, when you're doing this, did anything stand out to you as like kind of like a better or more interesting extension? Because like people have been trying to do this for like decades now, where they look at central banker things and they're like, oh, inflation's going to go up or go down, and then like buy bonds or whatever. So I'm curious if anything stood out to you where you're like, yeah, we can make this better or more interesting.
I mean, there are a lot of interesting approaches in the field of mechanistic interpretability of LLMs. So this paper, we're not trying to bash those. I think there's a lot of value here. I know you're familiar with Anthropic. They actually came out recently with an interesting paper that does, I guess, a more sophisticated, has a more sophisticated take on mechanistic interpretability. They use a dictionary-based approach, not simply linear probes, and they're also quite careful to not draw any crazy AGI conclusions in general. In terms of, actually using LLMs in this context of central banks, we did present this work earlier this year in London at a conference organized by central banks and King's College London. And what I see is that a lot of central banks, especially the Fed, are very actively investing in this work, in this type of work. So the Fed is working on their own sort of BERT-based large language model to quantify their own communications, which is interesting.
You're like Jerome Powell. You're talking too much. Slow down.
Exactly. So I can see many use cases. I can see central banks using this to sort of navigate, as you say, navigate their communications. But the common challenges. To what extent can you then actually, trust that your large language classifier, your hawkishness indicator, is actually accurate, is actually trustworthy? Lots of work to do then in the explainability space, I think. But to answer your question briefly, lots of people are interested in working on it. Yeah.
All right. Thank you.
Any other question? All right. Then let's conclude this session. Just a reminder that you're free to go to the PyData talk as well. That will start in about 10 minutes. Then we'll come back in this room at 3. Thank you.
Thanks.
All right. Should I get started? Or?
All right, let's start this next session with Philip from Akamai. He's a principal RAM distiller, and he will tell us how to use Julia for this anomaly detection pipeline. Right?
All right.
Anomaly.
Yeah, anomaly detection. All right. Well, hi everyone. Still a few people coming in, but thank you for being here, especially because there are 6 other talks happening at this time, which are all pretty awesome. There's also a BOF, so thank you for choosing my talk over all of the others. My name is Philip, and I work at Akamai. In case you don't know, Akamai is primarily a CDN. We run about 90% of the internet traffic through our servers. My team works on a product called mPulse. It does real user measurement, so we collect performance data from users as they browse our customers' websites. And we've been using Julia to do parts of this analysis since Julia was version 0.2. It's quite a while ago. I live in Cambridge in the United States, not in England. This is not Cambridge. This is Boston when you're standing in Cambridge. Right? Boston has more lights at night, so it looks better at nighttime pictures. I bake bread. Sometimes I take part in competitions, and I have never won, but my scores have been slowly increasing. This one is my competition bread, which I think fell right in the middle. Now, bread is handmade, and the way it grows depends on 2 microorganisms, yeast and lactic acid bacteria, one for rising it, one for giving it flavor. And you have to get the balance just right to actually have a good loaf. But also because of this dependence on microorganisms, because of its handmade nature, because there's water in it which evaporates when you put it in heat, the final product is not determinable by things when you start out. So you don't exactly know what it's going to look like, how much it's going to weigh, etc. when it comes out. You just have to hope you get the best. And so that actually brings me to an interesting story. It's very relevant to this talk, as the curious case of the abnormal loaves. Right, so let's see. I want to tell the story. I don't know if it's true or not, right? But it was fairly interesting to me with the statistics background and the baking background. So I wanted to bring it up. After World War I, in Germany, bread was rationed. So you could get 1 loaf of 1 kilogram each, and that was your ration. So now, because of this handmade process, a 1 kilogram loaf is not exactly going to be 1 kilogram. Sometimes it'll be less, sometimes it'll be more. In fact, it follows a normal distribution. If you take all of the loaves baked in one day and you measured their mass, they would fall on a normal distribution of mass, and the center should be 1 kilogram, the median or the mean. In case of a normal distribution, they're the same. So this mathematician, a math professor in somewhere in Germany, I don't know the city, decided to measure the loaves that he was receiving every day. And it turns out it was a normal distribution, but the median was not 1 kilogram. It was below 1 kilogram. And so he hypothesized that the baker was probably stealing some dough from every loaf to make a few extra loaves for himself or his friends or something like that. And so he confronted the baker and said, hey, your process is wrong, or you're doing something wrong. So the baker essentially adjusted his process, and now when the mathematician started measuring the loaves, every one of them was more than 1 kilogram. So problem solved, right? It turns out not quite, because when he looked at the distribution, right here, you see that it's no longer a normal distribution. It is the right-hand side of a normal distribution. So knowing the distribution, he could tell that the baker wasn't actually fixing his process. He was just making sure that he was only delivering the heavy loaves to the mathematician and the light loaves to everyone else. So essentially gaming the system by fixing what is measured and not fixing everything else. So by knowing the distribution, he knew that there was an anomaly here and that the fix was not actually fixing the problem. It was just fixing the measurement of the problem. So the lesson for me here is understanding statistics and the expected distribution of your data is important to anomaly detection. And luckily, Julia is very good at doing distributions and fitting data to distributions and knowing whether things match or not. So a lot of hypothesis testing is all good in Julia. So impulse, kind of the same, right? Only we use web performance data instead of the mass of bread. So I'm going to very quickly give some background on impulse because I'm guessing most people here do not have a web performance background or have never seen impulse before. What we do is we collect web performance data. There's a JavaScript library called Boomerang that sits inside the web page of our customer sites. So we don't have a site. Well, we have a site, but nobody uses our site. Our customers have websites, and they put our JavaScript on their website. As a user browses their website, it measures how long it takes for the page to load up, and it sends that information back to our server. So there's no personal information about the user, just the performance of that browsing experience. And that's beaconed back to our performance analytics application. It's called Impulse. It's written in Java, but there's also a Julia interface to it called impulseapi.jl. You can add that. It's in the registry. The data in the Java process is clean, filtered, sorted, and then it's streamed to various backend services. So one of them is our data warehouse where it'll be stored for a longer term. Other parts do anomaly alerting, visualization, and then there's also a Julia backend which has advanced data analysis and some amount of visualization. So at a high level, this is kind of what this looked like before we added the anomaly detection component. Right, so the website users up there, Boomerang is written in JavaScript. Impulse and the stream processing are written in Java. This advanced analytics component is written in Julia. And we hope the end users are human, right? With the paying ones, the customers there, we know for a fact whether they are human or not. They do have automated jobs, so there will be bots. With the end user using the website, we don't know that for a fact, so we have some kind of bot detection. Again, anomaly detection plays a big part in knowing whether the user using the web is a bot or human. Right. So, in terms of the timeline, just to give an idea of the maturity of the project and why not everything is written in Julia, because if I looked at it now, I'd say everything except the JavaScript part could have been written in Julia. But we started in 2010. Julia didn't really exist at that time. Right? I publicly released Boomerang just to collect web performance data. There was no backend for it, so you would install it on your own site. You would collect data in your HTTP access logs and do something with it. In 2011, we built a precursor to Impulse. At that time, it was in Node.js, but we quickly moved to Java and sort of scaled it out both vertically and horizontally. In 2014, we added the advanced analytics capabilities in Julia. And at that time, Julia was 0.2. So things were changing very quickly with Julia, but our code base was fairly small. So we started with 0.2 and we migrated to 0.3 and 0.4 by 2015. So just in 1 year, we actually migrated our code twice to 2 versions of Julia. Then we kind of got stuck because we started adding all of this code. In 2016, we added this anomaly detection component, which is what I'm talking about today. And the number of customers that wanted that feature was quite a lot. So there were a lot of people dependent on the Julia code now, and we could no longer upgrade. So we were stuck on version 0.4 until 2023. That's last year, right? To give you some context, 1.0 came out several years ago. 1.6 came out several years ago. That's a long-term support. In fact, 1.6, as of this conference was announced, will no longer be long-term support because 1.10 will be. So I have a talk tomorrow about just the migration process. But the feature is kind of a year old, but it's also been maturing over several years. Now, the data we collect is mostly time series, so multiple users requesting web pages. We get performance data, we get beacon volume data. It's related to real user experiences. Each data point has multiple events. So in all, there might be about 500 different dimensions and metrics on the beacon. And it's like, when did the first byte come in? When did the first large thing on the page get drawn? When did the page complete loading? When the user interacted with the page, how much time before the interaction actually did something on the page to not frustrate the user? Because they're real users, it's an uncontrolled environment, kind of like the yeast and lactic acid bacteria. They're doing all sorts of things. Different users do different things. They have different kinds of devices. Their devices have different kinds of things installed on them. And so we can't know what the environment is like. We just have to look at what the expected distributions would be and try and figure out whether things are going normally or not. But because we have all of this data, we can render individual waterfalls. So this is a waterfall of one single page. This is a fairly simple visualization based on the data we have. It's done in the Java application. But we can also do multiple waterfalls. So we combine, in this case, about 1 million different waterfalls into one. And for this kind of analytics, you need Julia. So it's much slower, but largely because we're fetching a large amount of data from the database and then tying that all together in Julia. And it needs to match certain distributions. So that's what we'd show the customer. And then we can do time series, but there's obviously, visually we can tell that there's something wrong with this time series. Right? There's this real little peak over here that it looks like it's out of bounds, but if we look at data over time, this is fairly close to the peak that we would expect in a day. The problem is it's not an expected peak at this time of the day. I've taken out the time values because it doesn't matter for this presentation, but we might see this kind of a peak, but we might not see it so sharp. We might see it more smoother, we might see it get up there and then slowly taper off. So it shouldn't be expected at this time of the day. And unfortunately, Java is not that good at looking at all of this past data and saying, this thing does not look right, the way that you and I can look at it visually and say, this thing does not look right. We have a much stronger processor than would be written in Java. So the Java process has a sliding window. It stores a small amount of data in memory, just what's required to visualize. So over here, it would have that much data in memory. And it can't look back in time very quickly to tell you that this thing should not have been there. It's used for dashboards, used for API calls, and alerts. But like I said, it doesn't know anything back in time, so you would have to tell it what to alert on. Right? I could tell it, alert me if everything went above this level. But on the course of a normal day, could be a Wednesday, could be a Thursday, I might expect my normal traffic to be there. So that's not something I can just tell Java to say, alert me when traffic goes above this level. It's good at applying a set of quick arithmetic rules, not so good at figuring out the rules on a large data set. So that's where we wanted to bring in Julia. Because Julia is great at processing large amounts of data, especially columnar data. So even though we have 500 different dimensions, we may not need to look at all of them to determine what the expected values are. We can look at a few of the columns together and figure out what's normal and what's not. It's good at doing matrix multiplications, again, because we can do them columnar. There are already modules for doing Fourier analysis. So especially with time series data, it's cyclic in nature. You do Fourier analysis, essentially treat it like a digital signal, and you figure out the different components of that. You can do regression analysis, hypothesis testing, curve fitting. All of that is very easy with very little code in Julia. Right? You can also try out multiple algorithms in parallel. So you can start up a thread and say, I'm going to test out this algorithm with the data, this algorithm, and run them all, and then see which one gets me my best fit. And then tell Java, you know what, this algorithm worked well for this customer's data set, for this particular metric that you're looking at. And so go ahead and use that. But it's not something we want to start up on every request. We keep talking about time to first plot. That is come down a lot, but it's still measured in order of seconds. Whereas we need responses in the order of microseconds or milliseconds. Right? So I cannot start up a Julia process on every request to figure out whether something is an anomaly or not. I want to be able to do this over a longer period of time and then tell my Java process that's already running, when you see something that's out of this pattern, that's something to alert on. So remember this diagram that we had earlier, we essentially added this little component. So did not change the architecture too much, but we added our anomaly modeler in here, which essentially takes now all of the data which comes in, so through the stream, it also gets fed to the anomaly modeler. And that thing looks at multiple algorithms for different metrics that the customer cares about. And when it figures out the right algorithm, it'll tell Impulse, go ahead and use this particular algorithm. So it could be as simple as this is the expected IQR of a minute, right? So you get all of these data points for a minute, which could be, let's say, 1,000, 10,000 data points in 1 minute. Just do your P75 and P25 on that, figure out the IQR. And if things are outside a certain range, then that is an anomaly. That's an alert to be fired. Or it could be a more complex thing where it gives you the entire, let's say KNN ICAD is another algorithm we'd use, where you'd have the matrices that you need to multiply and then tell Java, go ahead and apply that only on the small data set of 1 minute rather than looking at 1 month of data. And so Java can do that kind of small amount of data processing very quickly. But it needs to know which one to use and on what data set to use it. So that's where we tie the two together. And so what we end up with is a better, I don't know if it's visible, but there are bands here. So what our anomaly modeler has done is for the same data set, it said you have an upper bound and a lower bound of the expected values of the data for every minute of the day, right? And this might change for weekdays and weekends. It might change for repeated events, holidays and stuff like that. And so this alert, this event that happens here is out of bounds because the bound is over here for this point of time, whereas the bound is up here for that point of time. And so this is an anomaly at this point of time, and it's fired an alert. Now we'd also notice may not be very clear, but there are like 2 points there where it kind of stretches to the edge and might be exceeding the bounds. But the other thing is that you might exceed the bounds for 1 minute, but that's not necessarily an anomalous event because it could be something that's unique to this day. Whereas if you exceed the bound for multiple minutes in a row, then that's more like an anomaly. So in this case, we have 1, 2, 3, probably 5 minutes when it's exceeded the bounds, and therefore we define it as an anomaly. And so this is the kind of things that this visualization would have been done in Julia versus this visualization which is done in Java. So this is all this is doing is taking the count star over time and plotting that, right? This is doing this count star over time plus figuring out the IQR for multiple months of data and plotting all of those together on the same chart. So if we zoom in a little more, this is more about the details of how we did the architecture. So we already had Jupyter. We were using notebooks to do a lot of our analysis. So I said, why not reuse Jupyter to do this? But we don't want to send, don't want to allow arbitrary code to be sent through Jupyter. Right? Jupyter will allow you to type in any code and it'll send that to a Julia kernel, which will execute it. We don't want the customer or somebody who has access to that to send arbitrary code through a web service that runs on our server with our data. So we modified Jupyter a bit where it only accepts JSON. Right? You can send it configuration saying, I care about this particular customer's data, and we can use authentication to figure out whether the person requesting it has access to that data. And then I care about these particular fields. I want to see data from Chrome, from this particular country, and I just want to look at the page load time, or I want to look at the total traffic. And so what Jupyter will do is it'll start up a Julia kernel, and it'll pass all this configuration back over to Julia. Julia will say, okay, thank you, I've received that. Please let the Impulse know that I am going to start processing it, and that's it. So it's send the request over, and then the response back is saying, yes, I've got it. Once that happens, the Julia process may or may not start up multiple threads to run multiple algorithms in parallel. Look at the data. Given the filters, it'll look at past data and try and figure out the different parameters for the models. And once it has figured that out, which might take, in the fast case, it might take a few minutes. The slow case, it might take up to 6 hours. And nobody cares because nobody is waiting for it to respond. Right? It'll tell Impulse, I'm done with this. This is what you should do to figure out if there's an anomaly or not. And now Impulse already has that data stream in memory, so it can immediately start applying those rules. It might have 1 hour's worth of data already, but it only needs to look at the latest minute. So it'll say, all right, let's apply these rules to the latest minute and see was there an alert or not. So from the time to defining something as I want to be alerted on this to actually being alerted, it could be pretty quick, a couple of minutes for the first alert, right? After that, it'll just keep happening automatically. Or it could be a couple of hours. And then the model will retrain itself every couple of weeks. So your data traffic might change over time, and it can retrain itself. So you don't need to know that it's retraining, because it'll take whatever time it needs to retrain, use the old model until the retrain is complete, and then run the new model as soon as that is complete. Yeah, and then finally, MPulse can send alerts in various ways, either using email or using Slack or calling a webhook or something else. So by doing this, we avoid code injection, right? I said a Julia application receives a JSON configuration, which checks to see if the keys and types of the elements in the JSON object match the method values. So we built a module called Method Inspector. Again, you can package add that. It's in the Julia repository. It essentially has 4 methods, right? Arg names, arg types, KW args, and KW types. You pass it a method, so not a function, but a method of a function, and it'll tell you the names of the positional arguments, the types of the positional arguments, or the names of the keyword arguments, and the types of the keyword arguments. And so we use that a lot to do this kind of introspection to figure out which method, or whether a method exists at all, right? When you pass in the JSON, does a method exist that can do that kind of modeling that has been requested by the JSON? And by doing it this way, we can update the Java code independently of the Julia code, and the Julia code independently of the Java code. So we discard anything that is unknown by the Julia side, and similarly, when we write back to the Java side, that can use or discard anything that it doesn't know about. We could, I think probably nowadays we could probably do that with Pluto, but Pluto didn't exist when we first wrote that. So the development process, and I'm kind of coming to the end of the talk here, but with the development process, we have our data scientists who develop all the algorithms for doing the anomaly detection. It's not a job that software engineers need to worry about. But software engineers need to worry about memory allocation and getting the algorithm to run fast in Java and being able to distribute it across multiple hosts. So once the data scientists have figured out the algorithm, built a proof of concept, and run it for a while, again, we can run it on a notebook server, or we can run it independently of the existing model. Then they will work with the software engineers to cut down that algorithm. So you may not need the full algorithm, right? An algorithm you're running on multiple months of data may be simplified to run on 1 minute's worth of data. So they will work with the software engineers to figure out the minimum viable algorithm for that amount of data that's it needs to look at, and say, all right, go ahead and implement this as efficiently as you possibly can to run in microseconds or milliseconds in memory. And then they define a specification saying, okay, this is how I'm going to send you the model. This is how you're going to request for a model. And at runtime, an algorithm is only used if both components support it. So for example, we could upgrade the Julia side to support new algorithms, but those algorithms will never be sent back to the Java side, because the Java side essentially tells the Julia side, I need a new model, but these are the only algorithms I understand. So give me one of these algorithms. But we can use it to test on production data, because we're not dependent on, don't need to send the new models back to the production system. And then once Java has been upgraded, it'll automatically start sending the new models if they're better, right? And similarly, we can deprecate all models in the same way. We can upgrade the Julia to stop supporting a particular model, and then it'll just no longer send that to Java. So in summary, as with bread, preparing the model takes way more time than consuming it, right? We need hours, minutes to hours to process the data, but we have microseconds to milliseconds to actually run on that data. You need to use the right tool for each step of the way. So in this case, we have Java that has everything in memory, that does a lot of jobs together. But we have Julia to do a lot of the heavy lifting that Julia is good at doing, that Java may not be good at doing. You need to communicate your process. So the two components need to be able to define a protocol that they're going to use to exchange data between each other. And finally, allow function calls to be mapped to JSON. I'd like to thank all of these modules on that side. The Julia Stats module, it's a organization. We use pretty much everything from there. Also DSP, data frames, data structures, and Julia itself. And there's a bunch of modules that we have released on our own. These slides are on pre-talks, so you don't need to copy that. You can download the slides and look at them. Thank you.
Any question? Yeah.
Hi, thanks. Could you elaborate on the methods you use for the anomaly detection?
Yeah. So I guess let me go back to the slide. So in this particular case, so we've used just a basic IQR method. So you have your time series over time, or your data over time, and we will look at by minute over multiple months and decide for each minute of the day. There are, we call it the IQR method, but there are various things to look at. So there's trending, and the data may trend up or down over time. So you need to figure out the trend line. Then there's seasonality. So that's why we'll use Fourier analysis to figure out the seasonality. Once we figure out those two components, we will extract them from the data. So we'll define the parameters. For trend, it's essentially a linear regression. So you get your y equals mx plus c. If you figure out your m and the c, you can store that in your model. Then you're the same with your Fourier analysis. You figure out the different frequency components and store that in your model. And then you're left with noise. Right? And that noise is your actual randomness over the course of time. So you figure out the IQR for that, the different percentiles. And you could have a tolerance. The customer might say, I want to be very sensitive, or I might want to be less sensitive. Or I might want to be very sensitive for these times of the day and less sensitive for these times of the day. So you can change your IQR bandwidth based on that sensitivity. And then when the Java process gets the same, it can apply the trend lines and the seasonality to what it has, and then look at the IQR of what's left over. Other cases, like I mentioned, is CAN and ICAD. That is a little more complicated to explain as an answer. There is a large research paper on that. You can look it up. It's just called K-nearest neighbors. I forget what the ICAD part stands for. So the clustering, there is Holt-Winters triple exponential smoothing, another way of doing it. Does that answer your question? All right. Any other questions?
Yeah.
What do your customers do with alerts when you trigger them or send them?
Yeah, that's a good question. So, yeah, alerts are useless if you don't do anything about it, right? One of the reasons for anomaly detection is customers need alerts. They need to know if traffic is going spiking beyond. Now, in this case, it's traffic. They may not care so much if traffic is going up. That may be a good thing. They do care if performance is going down, right? So if the load time is going up, that's something they want to be alerted on. Or if the time between a user clicking on something and the page responding takes too long. Or if the number of purchases have dropped, or the number of times a user converts has dropped. Those are the things they want to know about pretty immediately. Even if it's at 4 a.m., they want to know users normally buy, let's say, $1,000 worth of stuff right now, but they're only buying $100 today. So that's something you want to wake up for and check. Maybe something on your server is broken or something else. We can tie that together. So this is just looking at one metric, but we can look at other metrics and do correlation analysis on that and say, hey, you got alerted on this, but these are the other things that also changed at that time. So they could be related, and then they can be actionable. So the person who gets woken up with a page can decide whether he needs to escalate it or not. And generally the sensitivity and stuff, for different metrics, they might have different sensitivity values. There's also, like in the case of traffic, or let's say in the case of performance, you might care if the performance got worse, but not if it got better. So the bands, we can say ignore the lower end of the band. So even if it goes below the lower end, don't alert me. But I want to know the next day. So it'll send you an email that you can check in the morning. Maybe something went wrong, right? So sometimes a really fast page is a page with no information on it because it didn't load at all. So it might show up as really fast, but it's broken. We can look at JavaScript errors as well. That's another metric that they would look at. Yeah, but it's looking at what users are doing. So it only tells you that something a user tried to do broke, or something is going to break, like traffic is going up and your servers may not be able to handle that load.
All right, thank you. Any other questions? If not, then I have another question.
Yeah.
So in your model, you need to train it first, right?
Yeah.
Using available data. I was wondering, do you need to train with same type of data from the same customer, or you can reuse, let's say, already trained model for them?
No, we always do it same customer. It's mainly for privacy. We don't want to share data across customers, but also customers might have custom metrics and timers that only make sense for that customer. So like the same timer field might have a different meaning for different customers. So we can't use it across customers. What we can do is when we're doing broad research across the industry, we can say, let's look at all e-commerce customers together, or look at all financial institutions, or all newspapers, and look at as a whole, what does the industry look like, and then how does each customer compare to that. So those are things we can do, but we don't do that. So we don't offer that directly to customers. That's something we would do independently on our own research.
I see. Thank you. And how much data? Like you need, let's say, if you want to predict 1 hour, you need like a 1 week of data or something?
Yeah. Well, so typically we say 2 weeks because you want at least 2 weekends. If you have 1 weekend, it's not enough to figure out a trend, the weekend cyclicity. So 2 weeks is the minimum that we recommend. It can go up to 13 months of data. We don't store longer than that. Again, for privacy issues, we intentionally age out data after 13 months.
Okay, all right. Thank you. That concludes this session. Thank you.
All right. Thank you.
We have a 10 minutes break. right, let's start our next session. Please welcome Professor Pushmak from Warsaw School of Economics. He is also adjunct professor at Toronto Metropolitan University, right?
Yep.
And he will tell us how to use Julia to deal with data with OpenStreetMap.
Okay, thank you very much for this introduction. So I'm going to talk how to use Julia for special data processing, and I'm working on quite few libraries to cut things short. So I'm working with OpenStreetMap data, which is a kind of hierarchical XML data representing all world around us. It's built like of Wikipedia by thousands of volunteers around the world, and there is lots of information there. And what I'm interested particularly, I see this data as graphs, and I'm also interested in the metadata that is present there. Okay, so I'm working on the following three libraries at different speeds. Sometimes I'm focusing one on the other. One was abandoned project OpenStreetMap that I named OpenStreetMap X and revived it some years ago. Then I made some simple library for plotting. And then recently I'm writing a set of scrapers because it seems there is plenty of data in OSM formats. And if you want to extract some special data like from Google, if you want to find one restaurant, it's easy. But if you want to find 10,000 restaurants and you want to scrape, you get blocked by Google. And even if you pay money for extracting information about restaurants, businesses, places, etc., then they throttle it because they are very afraid of the competition and they just don't want to scrape all their special data. But this data is available in OpenStreetMap. So what I'm going to show is how to scrape it. So I have only 10 minutes, so I took the most crazy and risky approach. I have Jupyter notebook that has no resolved cells. So let's see if it's going to work. Okay, so how does it work? So the data, so I have prepared some OSM file containing information about the area around the haven, and suppose I want to plan. If I want to, for tonight, I want to visit all pubs in Eidenhaven. Okay, I want to visit each pub and I want to find the location. So this is the query. So this is some query. So this query is related to how XML data is structured, but basically there are key values, and pubs can be described as pub, as bar. And also I want to start here from the stadium just after the classes end, so I want to scrape also the data about the stadium. Okay, so this is the query, and then I run the query on the data. Now, this query mechanism is pretty kind of fast. It can do like 2 gigabytes per minute, which is, you know, and if you take a map of entire country, like a map of Holland, then it probably would take like a few minutes to scrape the entire map and have, for example, all pubs in Holland. But I just focus in the neighborhood area. So as you can see, I'm getting latitudes and longitudes of all pubs. Okay, I will be starting from the stadium. So this is the location of the Philips Stadium. So here we are at this building. Now I might also want to have additional metadata. So there is an additional parameter all tags that is extracting also additional pieces of information, like we have name of the pub, opening hours, and so on. This is going to be shown. I want to visualize it, so I'm changing this data to a dictionary. Okay, so this piece of code is changing it to dictionary, and now I'm going to recode the coordinates, because I want to make a plot of this map. So I'm using another library, OpenStreetMap X, to recode the coordinates, to read the map data. Now, what I do, I will calculate distances for each pair of pubs. One thing I didn't say, I think I filtered this data somewhere, that I'm just taking restaurants which are not further than 1.5 kilometers from the place. Oh, I do it here. I'm filtering this data to take the restaurants which are not further than 1.5 kilometers away using like city metric. Okay, so I'm also calculating a simple distance metrics. I could use actual roads for this, but just for simplicity, I wanted to calculate it fast. So I have now 40 pubs, and this 40 includes also the Philips Stadium, so this is the set of distances. So there is nice Julia library to find the travel path, and then I can I can load a Python library from Julia, which is named Folium and which is very nice, and I can visualize what I've scraped. Oh, and I lost the internet connection, and I'm not seeing the underlying map. Okay, so let me check if I can quickly connect again. So sometimes it disconnects. So there should be a map underneath. Blah, 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 blah. Yeah, so this is a live demo, as you can see, but maybe I can resolve it. I need to be fast. I have 4 minutes left. Okay. Because otherwise, we do not know how to work. Okay, so this is the plan. So here we start at the Philips Stadium, and these are all pubs within 1,500 meters. And then you can see these are all the data that we have just extracted using Julia for the OSM file. So you can see the amount of meta information is quite big. And basically any business information or any type information you can very quickly extract in this way. And I'm thinking it is about a tool for building large data sets for various types of analysis, because if I can scrape the data from maps, then we can do many types of analysis. So I'm doing agent-based simulations on cities. So my future goal is maybe to create a code for generating of synthetic cities. Like in graph analysis, we have generation of graph analysis. In agent-based simulations, we have synthetic populations. And here I might want to generate synthetic cities. Okay, so we have the map. And then another thing I could do, I could go slightly broader. So here I'm scraping from this data information about restaurants, fast food courts, bars, cafes, etc. And if I have this information, another thing I'm doing, I'm trying to aggregate this data. So I could make a plot that is describing the attractiveness of that area. This is also supported by this library, some measures for attractiveness of a particular location. So there's lots of research in the area of walkability city and how it's easy and how it's comfortable to go around the city. So this attractiveness of the area, Eindhoven, is here measured by the availability of pubs, restaurants, ice cream, cafes, and so on. And so in Eindhoven, it's easy. Everything is here. Okay, so this is how this library can be. This is how this library can be used for. This is how this library can be used for special data modeling. So you can see we start with defining what we want to scrape, and basically these are key value pairs. This is how just the data is being aligned, and then in this way, very quickly we can build huge data sets. And the goal of this library is to be able to process entire big areas, like taking the data, for example, entire country, and scrape out the addresses of all businesses and so on. So far before this library, my feeling is that mostly everybody was selling this data. So I had an idea to write a simple library to make this data for free. Okay, and thank you very much.
Any questions?
Excellent talk. I joined a little bit late, unfortunately. So I'm not sure if you mentioned earlier, do you have any parallelism to help you compute this in OSM toolset? And if not, do you have any plans for this?
Okay, so we have plans for parallelism. So one thing we are, thank you very much for the question. So the question was about the parallelism. So there is also additional functionality for tiling of maps. So basically, if you have, we have a map, and if it's a raw data like XML, a map is a 3-layered data structure. So the problem with the parallelism is the following: that in the map we have those three types of elements. There are nodes, which are kind of points. There are ways, which are sets of points, and there are relations. So it's a like 3-layer data structure. And this library is providing already quite fast tiler mechanism that you can take this XML of map data and then you can slice it into pieces. And it's sometimes not trivial, because how to slice the stadium in half or so on. So it's using some heuristics to decide which goes where. So there are plans for this, and it's something under work. Thank you.
All right, any other question? If not, let's thank the speaker again.
Okay, thank you.
So our next speaker is Christian. He's a senior data scientist at it's called LexisNexis, right? Yeah. So he's going to tell us how to use Julia for strategic data handling.
That's what the talk says. So, hello, Philip Stadium. Nice to see all 35,000 of you. Yeah, my talk is strategic data handling, or how to decrease time to ROI. You can thank ChatGPT for that title. So the motivation here is, in my role, time to ROI is much more important than fully optimized code or fully tested code, right? If I would be accused of wasting time if I were spending too much time doing those things. So when I previously worked in Python, I didn't have a whole lot of options to speed things up, just kind of use some general heuristics like use pandas and NumPy when you can, because I'm going to get C under the hood basically, or C++ or something like that, right? But Julia, has the option for, writing base Julia. It's already fast, so I can always consider rewriting something that I think is too slow in base Julia as opposed to dataframes.jl, and potentially get some speed ups there. So the question is kind of, how do I strike the right balance between spending time on improving the code and testing the code versus actually, getting towards my real business value goals. So I have 3 tips for you today. Let's see. The first one is to use Julia base types if it's necessary. If it's not, don't. Be empirical about which function is best. So you don't always need to know ahead of time or be able to understand why it's faster. Just go with what's fast. And if there's some critical piece of logic that you think might fail or might not work properly, test that. But you don't need to necessarily test everything in your code, right? That takes time. So the first one, I'd like to basically, remind me that data frames is really fast in a lot of instances, and it's getting faster all the time. It's harder and harder to contrive examples where it's not as fast or faster than just writing it in base Julia. And so I want to consider these 2 functions here, which both implement a cumulative sum. You don't need to do this. This is already implemented elsewhere, just an example, right? It's roughly the same. So I pre-allocate a vector, and then I iterate through it, and I create that sum, and I return the result, right? The main difference is on the first function, the top one there, we're passing in a vector int, and on the second one, we're passing in just a data frame and the column to tell which, a symbol to tell which column. So, but what I can see here right away is that in the top function, the compiler Julia knows at compile time what the types are going to be. So it can do a lot of specialization there and speed things up for us at runtime. For the other one, there's no way for the compiler to know what the type is going to be, right? We're just passing in a data frame, and every time it iterates through this, it has to then check and then do some dispatch. That's all expensive. So when you're iterating through this a bunch of times in a for loop, that's going to add up and be quite slow. So apologies for the kind of ugly looking slide here. Quarto is a love-hate thing for me. But what you can see here is that it's gotten a little slower actually, but roughly 100x change when we look at the mean here for the function in base Julia versus calling it on that data frames thing. So that's something that you can feel at the human level time scale, right? If this was 8 milliseconds versus 16 milliseconds, I might not care as much, because refactoring that code and testing it could possibly, I spend more time doing that than I wasted just running this. So the second tip is to be empirical, right? If there's a part of your code that is kind of a bottleneck, address that part and address it in a way that is just running the benchmarks as opposed to trying to figure out what's going on. So if we look at these 3 functions, I could try to think about why one of these might be faster than another, but that takes time, and I could easily be wrong about it. So again, roughly implementing the same thing, just slight variations. The first one, I can tell is probably going to be slow, right? We're instantiating a data frame, and then we're vcatting a bunch of data frames to it. That should be df. But so that, it's a mutable object. you can change types on any of those things. It's an expensive operation. I expect that one to be slow. But these two, I couldn't really tell you. You know, maybe the first one is faster. Maybe the second one is faster. You know, the second one is just tables, pushing all the tables into an array and then vcatting them and then turning it into a data frame at the very last step. The other one is creating a bunch of data frames and vcatting them at the last step. So I don't really know. I don't really want to think about it. I just want to run the benchmarks and see. So the first one, yeah, 32 seconds. We could tell that one was going to be slow. But the second one, 1.3, and the third one, 3.9, right? So it ended up being faster to create a bunch of data frames, an array of data frames, and then just vcat them. I might not have guessed that. And we could ask, why do we get these results? We could start analyzing that. We could run a bunch of benchmarks at different sizes and see how the function changes over, you know, the size of the input. But we're wasting time. This is not getting us towards that return on investment, and so why do it? Yeah, and then the third and final tip is it's much easier to test on base Julia functions than it is on, you know, something that's written on a data frame. So data frames, again, really great for rapid development. I use them every day. I'll write these long kind of chains of data frame operations, and, you know, from that kind of have some pre-processing pipeline. But occasionally I'm doing something in there that might be kind of brittle, or I don't know for sure that it's going to work every time. And so I want some guarantees about that. But I'm not going to test all of it. I'm just going to test the parts that I'm kind of concerned about. So if we look at this code, what you see is in the first pre-processing one, you know, we're selecting, and then we're transforming, we're making, you know, we're squaring this A value, and then we're applying this regex cleaning here. This is really the only line that I'm worried about, right? Like, I know a value times itself is going to be the square. I know that these other things generally work because that's just well-tested data frames code. So what I would rather do is replace this line with a function that operates on a string. And now I can test that individual function and be more confident that, yes, this does do what I think it does. So this one, you know, it's supposed to remove leading zeros, right, in this example, but maybe it doesn't work in every instance, right? So I want some guarantees. So I've wrapped that critical logic, and then here we can look at like the examples of testing, right? So the first one, it's just so much easier to test this. All I did was call the function, I put in a test, and I put in the value. It's very easy to reason about. The second one, it's kind of annoying, right? So I don't really care about the A values. That's not what I'm testing. I don't care about the C values, but I still have to create a data frame with all those things in them. I still have to run that larger process and then actually test those values at the end. So this can get really unwieldy as you start dealing with more realistic data processing pipelines. Yeah, so that's it. Thanks.
Any question? If not, then I have a question. Oh, yeah, you have.
My question is, can you tell us something about LexisNexis? What is this ROI you are talking about?
Oh, sorry, return on investment.
Yeah,
right?
I know, but
So LexisNexis is a legal software company. They make a lot of software for lawyers and so on. But really, in my role, like, it's very dollar focused, right? So the things that I'm doing have to be making the business money, and so it's really about like how quickly can I iterate, how quickly can I produce things that can have like that bottom line impact. It's not necessarily about having the absolute fastest code all the time, right? Well, those are things that we can think about and improve later on in the process if we go into production and all that. But, you know, really it's just get to the finish line with something that's good enough that doesn't slow you down as the human, right?
Right.
Cool.
So you give us some tips about how to speed code up. I'm just wondering, like, is it generally true that you want to write functions instead of directly manipulating your data frame?
Yeah, functions will typically give you a speed up.
And that's because you were specified the data type?
Exactly, right. So really what it's about is so the compiler can make good inferences about what types it's operating on. If it can't, that's going to be expensive.
Okay. All right. Thank you. Our next speaker is Adita. She specializes in data science and how that applies to the well-being of students. So she's going to tell us how to use Julia to monitor students' well-being.
Hello. Good afternoon, everyone. I'm Aditi Raviraj Purse, and my co-speaker is Radhika Bhangi. She couldn't come due to some traveling issues, so I'll be taking forward this presentation. So I'm pursuing education at in artificial intelligence and data science engineering, and I'm studying at Angdi Institute of Technology and Management at Belgavi, Karnataka, India. Today's my topic is forecasting mental wellness of students using Julia. So these are my contents. Introduction, significance of it, importance of mental health in students, Julia for mental health analytics, demonstrating a basic forecasting model, results and discussions, and the conclusion. So what is mental health actually? So it is a component of overall well-being of a person, how the person think, how he acts psychologically, mentally, socially, that affects his life, the environment he stays in. So that plays a very important part in every student's life. So here I know that each and every person of every age from small to big, each and everyone suffer from mental health issues due to stress, anxiety, depression. But I am focusing on only the university students. So the significance of it is accurately predicting the mental health issues. University can implement proactive measures to support students or reduce dropout rates and foster a healthier, more productive academic environment. This project not only aims to enhance student well-being but also contributes to broader understanding of mental health dynamics in educational settings. Here sometimes what happens is the problem will be not so big, but they make it so big by overthinking about the problem, and they make it so big that they get stressed out, and sometimes it results into something very bad which it shouldn't happen. So the student life, now I'll give my example. So I'm giving a talk here. Before that, I'll be having some nervousness that how it would be, how will I speak. Each and every speaker coming here will be having some point of nervousness that how it would go, how the people will take it, will they understand or no. I need to convey my message to the people in a very right manner. So these are all the stress factors the students will be having. And one more example I want to give is I don't know how many of you heard the news that a robot in South Korea maybe he did a suicide because of the overworkload 9 to 4 job. So my point is the robot should be given the work which robot give. If we give them one work, it can do one work. If we give them humanism, like if they have to work 9 to 4, it would be very stressful for them also. So the methodology in which I'm using in the project is I have taken some parameters based on which I can check the student is how much mentally well and how much he is ill. So the parameters I have taken is the academic performance, the attendance of the students, his social media posts, the overall curricular activities he takes part in. So I have used these packages: Flux, MLJ, data frames, CSV, random.gl, plots, and MLBase. So steps and algorithms, what I have done is I have taken a data set on based on these parameters. I couldn't get all the data set because it's very private, so I had to create a synthetic data set of some part. So I created a data set and I took some samples of it and converted into a CSV file and kept it in data frame. And then that is the data generation, data handling, and the data splitting. So I had to make those data sets. I have to make it in two partitions in it, that is the training and the testing part. Most of the part was for training and some amount of for 480 elements for testing part. Then I used neural networks for the algorithm to train and test the data set. So neural network built and trained using Flux to predict academic performance. Mean square error I have used, R2 score and the accuracy, precision, recall, and F1 score, performance metrics for the classification. The importance of mental health is the academic performance. If the student is well, he will perform good in his studies also. If he has no more stress, then he can perform well. He can take part in other co-curricular activities which will be held in the society. And the social relationships, he could be very much good in building a more good network with people. And the future prospects, under addressed mental health concerns in students can lead to long-term consequences affecting their future opportunities and the well-being. So why am I using Julia for mental health? Julia's robust data structures and libraries make it a powerful tool for processing and analyzing complex mental health data sets. Predictive modeling, Julia's machine learning capabilities allow for the development of accurate predictive models to focus students' mental wellness. Visualization, Julia's visualization tools enable the creation of informative and visually appealing graphs and charts to communicate insights. So this is the graph which I got. The actual part and the predicting part, that how much after the training and testing we could get the prediction of it. And the accuracy and the reliability, so I could get 0.95% of the accuracy. And the insights and trends, analyze the models output to uncover patterns and trends in student mental wellness, informing strategies. So the conclusion of this is proactive approach, personalized interventions, continuous improvement. Forecasting mental wellness can help educational institutions take a proactive approach to supporting student well-being, and personalized interventions by identifying risks at risk students. Targeted interventions can be implemented to address the specific mental health needs. Continuous improvement, ongoing refinement of the forecasting model and integration of new data can lead to more accurate and comprehensive insights. Thank you. Yeah. Why this? Okay, thank you for the question, ma'am. Actually, I have taken some parameters to know what the child is suffering. He's stable or he's not stable. So for those things, I have taken some parameters, that is the academic performance, his social media posts, and the attendance part. Uh, we can see in universities, ma'am, every time we have a semester part, I could check through that the students is doing well at this semester and went down in the next semester due to some reasons. It's their personal things, it could be the family issues or the friends, or we can see relationships this time matter a lot for such people. So it really matters in their studies also. So I feel that it is very important for the person to be stable, to make his career good, his future good. Thank you.
For example, those like you taken into account basically the history of that person, right?
Yeah.
Into account.
Yeah.
Now it works. So okay, so then in your data collection process, you would also record those information, and when you process data, you also take that into account, right?
Yeah, actually, I didn't go to the history and took the data set. I took it actually and took it real world. What I did is we could create some amount of questions, in which we had some sort of questions in which we could get by that how much percent the graph could be created through those questions, so we can understand what the person is feeling according to those questions.
Oh, okay. So in the design of your study, basically.
Yes.
Okay. Thank you.
Thank you.
Yeah.
With how much frequency per year would you be polling the students? Because, I mean, you could get depressed very quickly, I guess, if things are not going very well.
Actually, yes, right, sir. It's not static. Every time the percentage of students suffering from anxiety or the depression or the stress, it keeps changing all the time. So we can't predict that at what year how much percentage of the students might be suffering from it. So we don't have any accurate percentage for that, sir. It keeps changing. It's dynamic in nature.
But basically, you accept it as just a part of the
Yeah, every time it keeps changing, ma'am. Focus. I have kept the focus on the university students basically, because we being so much adults, we start learning, so we get that amount of patience in ourselves to handle the situations in well manner. We have to be emotionally stable to handle the situations. So we have more patience. So the university students, if they get something, some stress amount of stress, they go through some parts and it will result into a suicide, ma'am. We have seen many cases till now. So this is the thing.
Okay, great. Thank you. All right. Let's thank the speaker again.
Thank you.
So our next talk starts at 4:30, I believe. So we have about 15 minutes break. All right, let's start our next session. Yan is a decision scientist working at a pharmaceutical company, Merck & Co. So he will tell us how to use Julia to design cost-effective experimental drugs.
Yeah. Thank you very much, and welcome everyone. I'm very glad to see you here. And I will try to make this talk as engaging and as fun as it gets. But before we get to that point, let me first introduce myself. Yeah, I'm Jan. I am from MSD. We are also known as American company in the US, and we use Julia to save lives. That said, we are a pharma company, biopharmaceutical company, and I'm a part of a company or group of data scientists. We call ourselves decision scientists, and we use Julia and these mathematical methods to navigate and support the operations of our company, well, starting from preclinical research up to some clinical manufacturing and supply chain. And I would like to give credits also to my colleagues. So first to Otto Ritter, sitting here with the head of our group of decision scientists. Also to Sean Wu and Tenchi Chen, who are based in the US. And on the other side, to Sean Yu and Yuan Bo, who are also based in the US, and they are not from our group of decision scientists. Instead, they are on the side of the preclinical research. And for example, Sean Yu is a seasoned chemist, and together we try to to tackle these different and very interesting problems. And I'd like to again to thank all my colleagues. I know that some of them may be listening to this talk online, and yeah, it has been a humbling experience to work with you. So okay, so let me move to another point. So you may wonder what these cost-efficient experimental designs actually refer to. So I will tell you a story. Well, we can imagine the pipeline or the sequence of the steps we need to manage during the drug development as follows. So we start, or first we try to identify some promising compounds, the promising drugs. Then we need to test these drugs for the desired properties. And we can, of course, then adjust some properties of these compounds, but it's some kind of a filter. Like we start with many compounds and we filter these using many different triages and different tiers, and if they succeed in some tier, they follow into the subsequent tier, and for example they go from the preclinical trials up to some clinical phase, and if they succeed even in the clinical trials, they go to market. So but each stage, each bucket here is very, very complex. So let me zoom into the part of the practical research, and here even this single box, well, this is comprised of many many additional filters, of many steps that we need to take. We need to test the compounds for efficacy, for safety, and again, each of these layers is again very complex. So we started actually working on this, or the motivation for the development of this package was when working in the so-called PGP assays, and all the data I show here is just for example, the structures are the chemical structures of some Merck drugs. I took these structures simply for Wikipedia, so they are known, and also these so-called measurements. These are just some random numbers. So this is just for some illustration purposes. But anyway, the point is clear. Like you can imagine, this is what the bench scientist in in the preclinical research actually sees. So he has some compounds, and there are multiple like assays, like multiple experiments, and we have to run these experiments. And we want to predict, for example, some particular property of the given compound. Like in this case of the BGP assays, we want to measure the drug binding properties in brain and plasma. And yeah, there are multiple experiments which are correlated, and they all somehow they bear some information towards some ultimate assay, like the so-called KPU, which is on the last line. Yeah, right on the bottom. This is some ultimate experiment, some ultimate measurement that we want to get, but unfortunately, it's very costly. For example, to perform this KPU experiment. And instead, we may want to use some or utilize some proxy experiments, and then given the measurements or the readouts of these experiments, we may want to predict this target, this ultimate experiment. So, like, yeah, this is very complex. So. So we try to run some of these experiments, and then based on the outcomes, we may decide whether the compound whether it's promising, whether it should advance into the next tier, or whether we should really abandon this compound. And basically, there are some rules. Which can be used to differentiate between the promising and non-promising compounds, but there's some space, of course, for improvement. Like going from some static rules, we may want to create some adaptive decision-making processes where we are able to synthesize, for example, the different information which is available from these different experiments, and somehow integrate everything in a way that we don't really need to run all the assays to get all the experiments, but we want to run as few experiments as possible, so that we save some cost, and at the same time we want to maximize the information towards the ultimate experiment. So for example, yeah, here in red these are some NAs. So these are the experiments which were not measured so far, for example, and yeah, so we can, of course, use some predictive modeling to predict the outcomes of these experiments, which were not run previously. And of course, yeah, this is done in practice, but well, what's the current state, of these things is very simple, because, for example, the chemists only use some predictive modeling starting from the chemical structure of the compound, and then they try to predict the outcome of some given experiment. But we may want to use the already available compounds. Yeah, for example, here the results of these experiments, and combine these into some boosted predictive model, and to predict the readouts of the remaining experiments. So yeah, in some sense, we try to create some posterior distribution conditioned on all the available readouts, and to get some sharp or refined estimates on the on their experimental readouts. And this, of course, can somehow be done, if we have these kind of estimates, we can, simply plug in this into some decision matrix, into some decision-making matrix on the decision-making tree, and, for example, abandon the compound earlier or so. Yeah, so there's a huge space for improvement. So in general, like in our framework, we try to combine multiple ideas. So first, we try to approach the refined estimates or predictive models, and which predict the outcomes of some experiments given the outcomes of the previous experiments. So that's the first part, and the second part is like to set up the ordering of the assays, or to to set up the so-called research operation plan, which actually tells us how to run, or how to which experiments from these to actually run, and in in what order, and so on. So like our ultimate goal is to somehow automatize the entire cycle of drug development, where we design the drugs, make them, test them, analyze, and then based on the analysis we again inform the design of the next compounds. And I would like to to set up some very intelligent paths through this research operation, through these research operations, in the way that we can we can pick the next experiment which we run, and then we can somehow predict the possible outcomes for the experiment, and then we somehow already can have some estimates on which experiments will be run next, given the different possible outcomes of the first experiment, and so on. So it's like playing some chess game where we have some possible moves, and in our case, we have some possible moves. Then the opponent takes his move. So the opponent here, this is the outcome of the experiment, which is non-deterministic. Obviously, like we can only predict the outcome of the experiment, and then based on the outcome of the experiment, we want to make the subsequent move. And of course, we want to somehow to hedge against the different possible readouts or the outcomes of the experiments. So it's sort of like setting some chess playing engine or so. And also, of course, there's space for improvement. Also, it's motivated by the fact that the computer can much easily wrangle with this huge complexity and correlations of between the different assays, and it can uncover these correlations and work with them very in some smart way. And for human scientists, this is much more difficult, and it, in practice it requires some extensive training. So this is costly, and we want to avoid this. Okay, so to that end, we developed this framework, this package we call the cost-efficient experimental designs. Here's some artificial definition of what I mean, by cost-efficient in this context. So, like as I said, we want to get as much information with the least possible cost. So we try to minimize the cost necessary to obtain the given amount of information. At the same time, we try to assess the cost-benefit ratio of the possible experiments which we can run. And the third bullet, this relates to the idea that I referred to on the last slide. So we want to not just pick one single best experiment which we are going to run, but instead we are trying to have some game plan, like so if we take this experiment, we want to already know have some projection or some idea what will be the next steps. So we try to make it in some clever way. Okay, let me now give you two examples. So I will use the glioma grading dataset. This doesn't really, this be different from the preclinical dataset that we are using internally, but we will be applying this seed designs algorithms to this dataset as well in the area of drug safety. And basically, we can restate the problem as follows. So just imagine we have some population of patients. We measure some genetic mutation factors for them, and we try to predict, or we try to classify the grade of the tumor, of the glioma, for the patients in this population. And there are two types of these tumors. So it can be lower grade glioma or glioblastoma. And yeah, we want to try to classify this given some clinical features, for example, age or gender, and at the other hand, using 7 mutation factors. And yeah, these 7 mutation factors are something like, yeah, we can observe them, we can measure them, but at the same time, you know, we have to pay for them. So we try to, we would like to measure as few factors as possible, but still get some accurate prediction or classification. So at this point, like our algorithm can take yeah, the general data set of the past outcomes for the population, of the past measurements. We can also, like this is shown here, we can you know, annotate the different experiments which we can take. Each experiment is associated with some cost, and yeah, each experiment actually yeah, it leads somehow to, you know, to observing of some given feature in the data set. And we can now, for each subset of these experiments, we want to quantify the information gain of this subset. And like, we can do this simply by using, for example, some classifier from the MLJ library, and we simply use the yeah, the predictive accuracy of the given model as the proxy for the information gain. And then given these you know, these estimates on the predictive accuracies, yeah, here we can set up so-called Pareto efficient frontiers. So like, let me explain this. On the x-axis, this is the cost of observing or running the given set of experiments, and on the y-axis, this is the predictive accuracy associated with the subset of the experiments. So this is a very interesting plot in the sense that, for example, you can see there's a huge gap starting from this yeah, between this blue and this light green point. So in some sense, you can see, or you can guess that, yeah, it makes sense to, yeah, for example, to execute the experiment or the subset of the experiments corresponding to the light green point. Yeah, in the sense that, yeah, we pay yeah, more, definitely more than for the blue experiment, but at the same time, you know, there's a huge you know, gain in the predictive accuracy. But at the same time, for example, between this light red and this red point, you know, there's a huge gap in terms of the combined cost, yeah, in terms of the cost, but the the information gain, or the gain in terms of the predictive accuracy, is not as large. So yeah, this is some very nice plot, and yeah, for example, if we were if the task was were to, for example, to decide which experiment to run, so yeah, we would say like, run this a light green or the green one. So yeah, we get some nice accuracy, and the cost is still limited. But of course, it depends on the specific context and on the demands that, for example, decision makers actually have. So yeah, we may, for example, if we have some lower bound on the accuracy, we may simply need to run this red experiment. But yeah, this is some kind of archetypical image or plot that we are dealing with. Yeah, another interesting part is, for example, is that we can use this C Designs package, for example, yeah, in this still in the same context, to measure the predictive gain if we, for example, introduce some extra feature. So, for example, this is still in for the glioma grading task. So we have the gene mutation factors, but we can also consider, for example, adding some histopathology image analysis. So yeah, we can simply run some CV algorithm and get some prediction from this algorithm and combine this with the genetic mutation factors. And we may ask if this if the inclusion of this additional feature, whether this leads to some improvement, of the predictive accuracy, yeah, whether it somehow shifts the plot. And of course, we can somehow associate this additional feature with some cost again. And for example, for the values of the cost and the predictive accuracy that I selected here, we can obtain the front as here. So like this is the front for just for the gene mutation factors, and this also includes the image analysis. So like you can see that by including the additional feature, we can achieve at the same cost level, we can achieve higher accuracy and higher information gain. And yeah, this this is a moving image. Yeah, this is animated. So here I simply simulated different sensitivity specificity values for the new CV feature, and also different values for cost. And I show actually how the efficient front of the decisions, how this shifts. And yeah, so this is very interesting. Like for example, in the context of pharma research, like we can use sort of these plots to assess whether we should, for example, develop some new detectors or some new experiments, and whether these experiments, because they are associated with some additional costs, yeah, whether this will actually increase our productivity, or whether it's worth it or not. So that's it. So basically, in this first part, so this is like one flavor of the seed designs package. So in this part, we assumed that we have some population of the patient, we have some measured values, and now like the algorithm can suggest which experiments to run for some next population of patients. Yeah, we assume that the next population, the coming population, will again follow the distribution of the previous population, and we want to to predict or classify the glioma grade for each new incoming patient. So like we set up some static design, some static ROP, which is in the sense that the triage or the different steps that we take are the same for all patients in the population. But we can do something more clever, of course. So let me consider this information value matrix. So yeah, we can assume like we have some experiments A, B, and C, and we have two subpopulations of some big population. And for example, we can assume that the experiment C, yeah, this is the information value, yeah, and that all the experiments have the same costs. So this is the information value or the information gain associated with experiment C, for the entire population. And we have experiment A, which has this higher information value for the subpopulation, but with very low information value for this. And yeah, the same here. So like like the idea is to dispatch on the specific population that we are testing. And for example, if we have population A, then we should run experiment or population 1, we should run experiment A, and for population 2, we should run experiment B. And we will achieve at the same cost, we will achieve a higher information gain. So to that end, yeah, we developed a so-called implicit Bayesian MDP algorithm for predictive triage. And in this experiment, we take some past outcomes of the experiments at the input. We also consider the different costs associated with the experiments, and then we try to set up the predictive triage, like playing the chess, for each particular compound or patient that we are trying, to test. So we have some current states or some evidence available for the given tested entity, and we can decide between the different actions that we can take. So like this is the yeah, the S and A, these are the mutually disjoint subsets of the actions which we already took and which we may took in the future, and then based on the previously available information, we try to predict or to estimate the likely outcomes of the experiments which were not run previously, and And then again, we try to to set up in the MDP fashion, like the predictive. We try to set up the experimental design in the sense, like this is the search tree, for example. So we start from some initial state, and then we decide which experiment to run next. So there are different options for the experiments. Then we sample the different outcomes given the posterior distribution. We sample different outcomes for this experiment, and then again we do the same. And the general idea is to somehow to achieve some given uncertain threshold, like we have some some good guess given all the information that we accumulate during this process, but we want to minimize, of course, the cost and the number of the experiments which we have to run. So to that end, we use the POMDP's package and the MCTS Monte Carlo research algorithm to do the search for us. So in the C designs package, we define the bindings from which define, for example, the transition functions and different sampling functions. For example, the sampling from these posterior distributions and so on. And if you are interested, you can also review our preprint, which where we apply these algorithms, this IBMDP algorithm to the specific context of the PGP essays. There's also a matrix or some table which compares or which shows that we can achieve some cost savings in practice by using this algorithm. And there are some other figures like pertaining to the specific PGP essays case. Like, for example, here we use some this illustrates how the posterior distribution about the target essay changes as we accumulate new information. So at the beginning, we have no experimental evidence, and somehow we have the highest uncertainty. And as we achieve, or as we gain, or as we run the additional experiments, we are able to to refine the estimates and the predictions, and somehow to have some more focused guesses on the actual properties of the compounds. And that's it. That's for the second flavor of the C designs package. So we have two algorithms. The first algorithm is for some static design that all the patients or entities will flow, and the second design or the second flavor is where each entity or each compound has some specific experimental design, and so we can dispatch on the particular properties of that entity. And I just wanted to mention, so this is this is from my last year's talk in Cambridge at MIT. This is this package, and the C designs package is a part of a larger ecosystem that we develop at Merck. And so first we have a package called Reactive Dynamics. This is for some expressive process modeling. It's like using some syntax of chemical networks, but to model business processes. We also have a package called algebraic agents, the JL. This is like agents of JL, but you can put very different problem modalities together. For example, you can combine some ABMs with some SDEs and so on. So it's really used for some simple approximation, but it's very nice that you can put these different types of problems together. And we are working also trying to put all these different parts together and model the entire pipeline. So this is the this is the figure from the beginning of this talk. So each box somehow corresponds to some very complex process in pharma R&D, and we can use our tools to approximate these different to approximate the dynamics of these different boxes. And so for example, we can, for this part, we somehow generate some, or we define some generative process of the new molecular entities. There can be some other part where we set up how actually some static triage or some static ROPs actually look like for these compounds in discovery. For preclinical, for example, we can use C designs, to run these to run these adaptive ROPs, and we can also, for example, consider some part for the latest stage of development, and we can, for example, model the manufacturing of the drugs, and so and we can like put everything together. It's just for some simple approximation, but if we have these these guesses or these estimates, like we can then iterate and go deeper and refine these models. So it's only used for some simple approximation, and but it's very powerful. Okay, so that's all from my end. Thank you.
Thank you. Any question from the audience? If not, I have a question. So I can imagine the process must be very complex, involves many different steps, and also different, let's say, compounds. If I apply this algorithm, and do I need to refine every time?
Yeah, it quite depends on the quality, for example, of the data. So so the easiest case would be like for the static design. This is the first part that I presented, and for the second part, for example, you have to, it's right that you have to, for example, so properly define how these posterior distributions should look like. So we use some for example, some weight functionals, which weigh the distance, or they estimate the distance from one particular compound that we are testing at this moment to the compounds that we tested in the past, and we try to use this distance somehow as a weight for the posterior distribution, and you can play, for example, with how to set up these weights, and so it may require some effort for fine tuning.
Okay. And how much data do you need, let's say, because you say there is an AI step, right?
Yeah, like we can start with few hundreds compounds.
I see. Okay.
All right. Yeah, but the more data, the better, of course.
Yes, of course.
Yeah.
All right. Thank you. That would conclude this afternoon session. Thanks, everyone.